the support of a conducive academic atmosphere, the actualization of ideas, and the research of several academics of the physics study program reached the final stage at the National Student Scientific Week, PIMNAS. Meanwhile, the recognition of the competence and expertise of the staff or lecturers were revealed in the contribution of aircraft acoustic testing in collaboration with PT Dirgantara Indonesia, development of fiber optic-based mobile mass scales tonnage vehicle in collaboration with Pusjatan, development of fiber optic-based natural disaster early detection systems for the Soloraya region, development of superior generation black rice in collaboration with Batan, and development of ventilator fan AG1103 during the COVID-19 pandemic in collaboration with BPFK Surakarta and other innovative products. In addition, it regularly organizes activities such as International Conference on Physics and its Application ICOPIA, the International Conference on Science and Applied Science ICSAS, and the International Conference on Advanced Materials for Better Future ICAMBF. With support from various parties as well as mutual or cooperation relationships in order to increase the quantity and quality of learning programs in the field of basic and applied science with the government institutions, the business, national and international industries, the undergraduate physics study program Faculty of Mathematics and Natural Science, Universitas 11 Maret, will continue to be committed to contributing the best in the learning process, especially physics, at the forefront of research and development of science and technology to provide quality education which produce good quality professional graduates in the field of basic and applied science in accordance with the needs of science and technology today and future.
UNS, MIPA, Fisika, Oke.
Undergraduate Physics Study Program, Faculty of Mathematics and Natural Science, Universitas 11 Maret, is a study program that organizes learning and research processes in the physics field.
Physics Undergraduate Degree Program, Faculty of Mathematics and Natural Sciences, Universitas 11 Maret, was established on 1996 based on the Minister of Education and Culture Decree number 0297/0/1996. This program was initially supported by teaching staff from many faculties within the university, such as Faculty of Medical Science, Faculty of Agriculture, Faculty of Engineering, and Faculty of Teacher Training and Education Sciences. Nowadays, the recruitment of the new teaching staff is considered based on the qualification of candidates through strict selection process. Learning and research activities of Physics Undergraduate Degree Program developed rapidly, which were funded by Development Undergraduate Education Project from Education and Culture Ministry. Now, Physics Undergraduate Degree Program has excellent teaching staff and facilities for students in gaining knowledge and research experiences in physics science.
Since its established, the undergraduate physics study program has taken an active role in the three Dharma activities of higher education, namely teaching, learning, innovation, leading in the development of science and technology through research, fundamental or basic research, and working for community service. and at last provide the best learning experience for students. The achievement of an A accreditation rating from Board of National Accreditation for Higher Education is the recognition of the education quality of the Physics Undergraduate Study Program FMEPA UNS.
Graduate profile of Bachelor Physics program in 11 Maret University who have met the learning outcome program can occupy several professions such as the first, researcher. Researcher who have the ability to implement scientific principle in research. The second, expert. Expert who has the ability to implement the scientific principle of physics. The third, educator. Educator who has the ability to transfer of knowledge in formal and non-formal education. The fourth, public servant. The public servant who has independence, work in physics and other science. The fifth, manager. Manager who has managerial skill and human research development.
The support of professional and competent human resources, as well as comfortable learning environment, is the perfect place for students to learn, process, and improve themselves. With a learning system that is controlled through a continuity of the quality of higher education, the Physics Undergraduate Study Program has supportive academic facilities to provide the best learning experience for students. In conducting classroom learning, practical learning in the laboratory, field-based learning, industrial internships, student community service, participating in national and international competitions, student exchange activities, both at home and abroad, the UNS Global Challenge, and student activities in the Physics Student Association or HIMA-FIS. The support of a conducive academic atmosphere, the actualization of ideas, and the research of several academics of the Physics Study Program reached the final stage at the National Student Scientific Week, PIMNAS. Meanwhile, the recognition of the competence and expertise of the staff or lecturers were revealed in the contribution of aircraft acoustic testing in collaboration with PT Dirgantara Indonesia, development of fiber optic-based mobile mass scales tonnage vehicle in collaboration with Pusjatan, development of fiber optic-based natural disaster early detection systems for the Solo Raya region, development of superior generation black rice in collaboration with Batam, and development of ventilator fan AG1103 during the COVID-19 pandemic in collaboration with BPFK Surakarta and other innovative products. In addition, it regularly organizes activities such as International Conference on Physics and its application ICOPIA, the International Conference on Science and Applied Science ICSAS, and the International Conference on Advanced Materials for Better Future ICAMBF. With support from various parties as well as mutual or cooperation relationships in order to increase the quantity and quality of learning programs in the field of basic and applied science with the government institutions, the business, national and international industries, the undergraduate physics study program Faculty of Mathematics and Natural Science, Universitas 11 Maret, will continue to be committed to contributing the best in the learning process, especially physics, at the forefront of research and development of science and technology to provide quality education which produce good quality professional graduates in the field of basic and applied science in accordance with the needs of science and technology today and future.
UNS, MIPA, Fisika. Oke.
Undergraduate Physics Study Program, Faculty of Mathematics and Natural Science, Universitas 11 Maret, is a study program that organizes learning and research processes in the physics field.
Physics undergraduate degree program, Faculty of Mathematics and Natural Sciences, Universitas 11 Maret, was established on 1996 based on the Minister of Education and Culture Decree number 0297/O/1996. This program was initially supported by teaching staff from many faculties within the university, such as Faculty of Medical Science, Faculty of Agriculture, Faculty of Engineering, and Faculty of Teacher Training and Education Sciences. Nowadays, recruitment
Okay, ladies and gentlemen, the conference will begin shortly. Please have a nice seat and make sure to mute your microphone. And I would like to remind you to rename your name with the following format: Zulu, paper ID, name. Example, 2154 Anasari. Okay, Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. A very warm greetings to each and every one of you. First of all, I would like to introduce myself. My name is Haya Alvinesa as the Master of Ceremony for today's conference. We are delighted to welcome you to the 11th International Conference on Physics and its Application, as well known as ICOPIA, that will be held for 2 days on 10th and 11th of August 2022. ICOPIA is a biannual conference dedicated to promote recent innovation and share knowledge in physics and its application, which proposes to foster international scientific networking and cooperation. It also aims to bring together researchers, academicians, and scholars around the world to share their research. This event is also potential to have a collaboration among researchers. And we would say welcome, and it's an honor to have you, Professor Ahmad Yunus, as Vice Rector of Academic Affairs Universitas 11 Maret. Good morning, Professor Ahmad Yunus. And also Professor Nuryani, as Chairman of the 11th International Conference on Physics and its Application 2022. Good morning, Professor Nuryani. And to the Honorable, our keynote speakers. The first one is Professor Dr. Muhammad Zamrun from Universitas Halu Oleo, Indonesia. Professor Dr. Markus Diantoro from Universitas Negeri Malang, Indonesia. Professor Dr. Idris Kabachi from Pusat University, Turkey. Dr. Francis Blake from Sheffield Hallam University, United Kingdom. Mr. Acep Purkon, PhD from Institut Teknologi Bandung, Indonesia. Professor Dr. Nafarizal Nayan from University Tun Hussein On, Malaysia. Professor Dr. Agus Suprianto from Universitas 11 Maret, Indonesia. Letkol Laut Dr. Dian Adrianto, MSI from Indonesian Navy Hydro-Oceanographic Center. And Dr. Andes Iwan Yahya, MSI from Universitas 11 Maret, Indonesia. And also, we welcome all the presenters and participants of ICOPIA 2022. We are heading to the next agenda, which listening to Indonesian national anthem, Indonesia Raya. Please have a nice seat and listen it with humility. Listening to Indonesia Raya. Thank you. Ladies and gentlemen, we are pleased to invite Professor Nuryani to deliver the welcoming speech as the chairman of ICOPIA 2022. Please welcome Professor Nuryani.
Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. Honorable Vice Rector for Academic and Student Affairs, Universitas Maret, Professor Dr. Ahmad Yunus. Honorable Dean of Faculty Mathematics and Sciences, and also the Vice Dean, and also Honorable Professor Dr. Idris Kabalsi from Turkey, is the international keynote, and also Honorable Dr. Francis Clegg from Civil Hallam University, the UK, Honorable Professor Dr. Nafarizal Nayan from Malaysia, and Honorable the keynote speaker from Indonesia, Professor Dr. Markus Diantoro from Universitas Negeri Malang, Professor Dr. Zamrun Firihu, MSc from Universitas Halu Oleo, and Asep Purkon, PhD from Institut Teknologi Bandung, and Dr. Dian Adrianto from Indonesian Navy Hydroceanographic Center, and keynote from Universitas 11 Maret, Professor Dr. Agus Supriyanto and Dr. Iwan Yahya. On behalf of the ICOPIA organizer, I would like to extend my warm welcome to all presenter, author, and also participant of the 11th ICOPIA conference. Also, I would like to extend a special welcome to our invited international speakers from the UK, Turkey, and Malaysia, and also our expert for keynote from Indonesia. Ladies and gentlemen, ICOPIA is a biennial conference organized by the Physics Department, Universitas Maret, and the author and also the presenter of this ICOPIA is from Indonesia and also from the offices. In this ICOPIA this year, the 11th ICOPIA, we invite experts from a variety of fields to speak at this conference, including the oxide-based optical glass properties, and also plasma processing and diagnostics, and also the polymer nano composite and other interesting topics. This year ICOPIA is conducted virtually as there is currently a coronavirus pandemic. And hopefully the next ICOPIA, the next 2 years, the ICOPIA can be held offline. About 100 research articles will be presented in this ICOPIA. And the paper will be published in the IOP, Journal of Physics Conference Series, and also the Journal of Evergreen. Finally, I would like to express my thanks to all who have helped to support ICOPIA. And we hope you all enjoy the conference today and tomorrow until the end. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Assalamualaikum warahmatullahi wabarakatuh. Thank you, Professor Nuryani. We are now going to listen to the welcoming speech by the Vice Rector of Academic Affairs Universitas 11 Maret. Please welcome Professor Ahmad Yunus.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Good morning, ladies and gentlemen. The Honorable, the Dean, Faculty of Mathematics and Natural Science, Mr. Dr. Arjana, Honorable Vice Dean, Professor Fenty Suryanti, Dr. Fahru and Dr. Dewi, and the Honorable Chairman of this international conference, Professor Nuryani, and the Honorable invited speaker, Dr. Asep Purkon from ITB Bandung, Professor Markus Diantoro from Universitas Negeri Malang, Professor Idris Kabaji from USAK University Turkey, Dr. Francis Clegg from Sheffield Hallam University UK, Professor Muhammad Zamrun from Universitas Halu Oleo, Dr. Adian Adrianto from Indonesian Navy Hydro Oceanographic Center, and also Professor Agus Suprianto and Dr. Iwan Yahya from Universitas 11 Maret. Distinguished guests, ladies and gentlemen, at this previous moment, let us first express our gratitude to merciful God who has granted us with blessing and grace that we could gather here to attend the 11th International Conference on Physics and its Application, which is this year organized by the Department of Physics, 11 Maret University. Let me extend my warm greeting and welcome to our distinguished speaker and participants, particularly from abroad. My heart welcome to Solo, Central Java, Indonesia. Although currently the number of confirmed cases of COVID-19 has decreased compared to last year, we are still holding this ICOPIA conference as online. But by not reducing our enthusiasm for sharing, I hope that this ICOPIA conference can be triggered to raise the level of our research a better level. This conference is important event. It is our occasion for positive contribution, idea, and knowledge sharing regarding the development of the future physics and its application in Indonesia, including in material physics, theoretical and computational physics, instrumentation, optics, acoustic, and geophysics. Finally, I hope all participants of this conference can find important areas of common ground on the best way for achieving the broad goal. I have great pleasure in formally declaring this convention is open. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Thank you, Professor Ahmad Yunus. Next on agenda, we will have a photo session. Please to our honorable speakers and all of our participants to turn on your camera. Prepare. Okay, thank you. Slide 1, let's take a photo. 1, 2, 3. Okay, next. Slide 2. Let's smile. 1, 2, 3. Slide 3. Let's smile. 1, 2, 3. Slide 4. Let's smile. 1, 2, 3. And last but not least, slide 5. Okay, that's enough. Thank you. Excellencies, ladies and gentlemen, we will begin the first session of plenary lecture that will be led by our moderator, Doctor of Engineering Risa Suryana, an associate professor from Physics Department, Universitas 11 Maret, to carry the session. Let me check you, Mr. Risa. Could you hear me?
Okay, clear.
Okay, then. Please welcome Dr. Engineering Risa Suryana.
Okay, thank you, Master of Ceremony. Assalamualaikum warahmatullahi wabarakatuh. Ladies and gentlemen, now we come to the first session in the plenary sessions. In this session, we have two scholars who will share their expertise. The first, Professor Muhammad Zamrun, and the second, Professor Markus Diantoro. Well, let me now briefly introduce them to you. Professor Zamrun from Halu Oleo University, Kendari, Sulawesi Tenggara, Department of Physics. He is a rector of Halu Oleo University now. He graduated from Universitas Gadjah Mada, undergraduate, and then master and doctoral program from Tohoku University, Japan. Professor Zamrun concerned about theoretical physics, and today he will talk about coupled channels formalisms for fusion reaction and quasi-elastic scattering. And the second presenter, Professor Markus, he from University Negeri Malang Institute. From University Negeri Malang. He graduated from Institute Teknologi Bandung, and now he is head of Institute for Resources and Research and Community Services, Universitas Negeri Malang atau LPPM. Ya. Oke, Prof. Zamrun.
Thank you.
Okay. Thank you, Prof. Zamrun. Okay, we have only 90 minutes in this session. I will share 40 minutes for each presenter. Then after that, we will have 10 minutes for question and answers. Okay, it is time to listen Professor Zamrun. Ladies and gentlemen, please welcome Professor Zamrun. Dozo, yoroshiku onegaishimasu.
Hai, arigatou gozaimasu. Okay, assalamualaikum warahmatullahi wabarakatuh. Is my voice clear?
Clear.
Okay, thank you very much. And very good morning for all of us. First of all, I would like to say thank you to the organizing committee for inviting me to give a presentation what I have done within around 15 years in my research about the theoretical nuclear physics, of course. Maybe in my presentation, of course, I will, if you see some equation or some picture, maybe you don't know, but I will try to give as simple as I can, and then you can understand all of that. Okay, ladies and gentlemen, especially Dr. Risa. He's my best friend. We go together in Japan, and then I don't know, but I come back. Earlier than him. He loved Japan very much, but I miss Indonesia, so that's why I have to go back to Indonesia very soon, of course. Okay, can I share my presentation? I guess yes. Okay, share screen. Okay, thank you very much. Okay, so okay. Thank you very much. So today I will try to give as soon as simple what I have done within 15 years in my research about the heavy ion reaction around the Coulomb barrier. Of course, today I will give you the result of my research within 15 years about the fusion reaction of quasi-elastic scattering. Okay, so before that, I have to introduce you where I come from. So I come from Southeast Sulawesi, Haloleo University in Southeast Sulawesi in Kendari City. So this is my place. You can come to my place. This is the left foot of Sulawesi Island, of course. So you can come to my place to Kendari from Jakarta with direct flight around 2.5 hours. So if you come from Solo, so you have to go to Jakarta first and then take the plane from Jakarta to Kendari. So, and then this is my campus. Our campus is with area is 2.3 million meter squares. It's a very big campus, of course, and then it's very green, you see. And then we have 15 faculties, and then one vocational program and one postgraduate program with a lecture around 1,700, and then student body around 40,000 students. So it's a big university. So we have many people in this university. So sometime please come to Kendari to Haloleo University, and then we can meet, we can share, and then we can discuss about the education in Kendari, of course. So today I will, the content of my presentation today is I will try to explain the basic concept of nuclear reaction, and then how to apply the concept of nuclear reaction to explain the experimental data of nuclear reaction, of course, and then success and failure, and then I will try to explain why the one-dimensional model to explain the experimental data of nuclear reaction is failure, and then we propose the couple channel method to explain the experimental data, and then I will give the application of the couple channels method to the fusion reaction and quasi-elastic scattering, and then I will summarize my talk. So in simple, the nuclear reaction means we have the projectile X and then the target Y, and then the target will hit the projectile, and then they will be interact each other, and then they will come to the state where they can combine each other. But the result of what we have to, the experimentalists, they measure the scattering nuclei, and then from that we can identify what happened in this that reaction. And then in the many lecture or in many books, they write the nuclear reaction like kind of this. For example, lead-208 plus oxygen 16, and then they will produce lead-208 and oxygen 16 is the same, but sometimes oxygen 16 plus lead-208, and they will we will have the new nuclei is the lead-209. And of course, in this case, we have one neutron transfer. This is the simple explanation about the nuclear reaction. So we have target and projectile, and they hit each other, and they will produce the new nuclei. For of course, if we have to, we have the target, and then we have nuclei. Of course, nuclei, they will have the proton, and they have nuclear proton. We know they have the positive charge. So if they come together, they come close together, they will form two force. The first is Coulomb interaction, as we know. If two charges come together, they will form the Coulomb force. Become here in classical physics, K1, K2, and then divided by the distance between two charges. And then this is very repulsive. And then the other one is, we know if you are in the maybe third years of graduate undergraduate, you will know about the nuclear force. So nuclear force is given in the Wood-Saxon form, is given by this equation. It depends also between the distance of the nuclei. So they will, if they combine to each other, the compensation between the Coulomb force and nuclear force, they will give what we internucleus potential. This is the, if we draw the Coulomb potential, is given by the green line, and then if we draw this equation, nuclear potential, it will give by the blue line. The combining between the Coulomb potential and the nuclear potential, they will give the total potential is given by the red line. So this is what we call is the Coulomb barrier. Okay. How the fusion and quasi-clustering happen? So if we have the target, and in experiment, we have the flux of the particle. So the flux of the particle can overcome the Coulomb barrier, and then some of the flux of the particle will be reflected by the Coulomb barrier. All is the reflected flux is known as defined as a quasi-elastic scattering, and then all their flux transmitted or overcome the Coulomb barrier is defined as the fusion. So quasi-elastic scattering as the fusion is complementary between the two. So it means because we have one, the total one, and then divided by quasi-elastic and fusion. So the total is unity. So that's why if we know the fusion, we can know about also the quasi-elastic scattering. What is measured in quasi-elastic scattering can also be measured in the fusion. So how can explain the experimental data? The three important, three important feature of FE-ion reaction is, first is the Coulomb force that I explained before, and then the reduced mass, and then the three one is the strong absorption around the Coulomb barrier. So the Coulomb barrier here. So this in this the green arrow, it means in the very strong absorption in this area. So and then one assumption. So the assumption of fusion is when the projectile and the target is touch each other, we assumption that the nuclear formation is happen. So this is the assumption. So the three, this one, and how can okay. So in the potential model, you know, this is the Schrödinger equation between the target and projectile, because here we have a reduced mass. The Schrödinger equation, in our community we call it the potential model. So we have to solve this Schrödinger equation. This is the potential. In this here, in this case, the potential is nuclear potential plus Coulomb potential, and then this is the moment and the kinetic energy, and then this is the centrifugal energy. So we have to solve the equation. Of course, we solve it numerically, and then because in experimental, they measure the fusion cross section. The fusion cross section means the probability that the fusion reaction is happen. So this cross section can be measured experimentally, and then our job is to calculate it theoretically, and then we compare between the theoretical calculation and the experimental data. So this is the result. This is the I take it from paper of physics report, very, very old paper, 1981. The line here is the theoretical calculation, and the circle, and then this open circle is the experimental data. So we see here for very light nuclei, we can explain the experimental data very well, but going to very heavy nuclei, the theoretical, the potential model calculation, the experimental data is different. They can only, the potential model calculation can only explain the experimental data in higher energy. It means above the Coulomb barrier. So it means work well for a relative-like system, but only predict the fusion cross-section for heavy system at low energy. So here is very, heavy high energy, and then this one is the very low energy. And then what makes the potential model is fail to explain the experimental data. Here the Coulomb barrier, Phoebe Coulomb barrier is around here. So the potential model calculation can also, can only works well, only explain the experimental data in this area, but in the below the Coulomb barrier, the theoretical calculation and then the experimental data is totally different. So what's the origin, the difference between the theoretical calculation and the experimental data? Now I will explain later. In this case, we have to include the channel couplings. We know from many books, the channel intrinsic excitation of the nuclei, they have the vibrational excitation and rotational excitation. To include this intrinsic excitation, we have to rearrange or make our equation, what we call it coupled channels equation, is given by this equation. This is the coupled channels equation. In the potential model, we just only have this kind of equation, but in the coupled channel equation, we have the coupling between relative motion and the intrinsic degrees of freedom. That is the vibrational excitation and rotational excitation. So in the potential model, we have only this, but in the coupled channels method, we have another term, this is a coupling potential, the coupling between the intrinsic degrees of freedom and the relative motion. And how we solve it, how we include it. So that means we follow the format Wood-Saxon potential introduced by Koichi Hagino and Rulli and Atekupra. Hagino is my supervisor when I take my master and PhD in Tohoku University. So it means we include the intrinsic degrees of freedom by the coupling matrix here. So the O with hat. And then the nuclear potential and the Coulomb potential. Nuclear potential without coupling, we don't have this term. And also in the Coulomb potential, we don't have this term. We just only have this. So how we include this and the coupling matrix? So the coupling matrix. So we have this. We have this vibrational coupling and rotational coupling. So we have to diagonalize this matrix first, and then we solve the coupled channels equation here. Of course, we solve it numerically. How can we do that? So we give the, yes, we solve our equation by using the scattering wave boundary condition is given by this. And then we solve that equation to calculate diffusion is given by this equation. And then we calculate the quasi-elastic scattering, a quasi-elastic cross-section is given by this. So illustrated, but we have the incoming boundary condition, we have scattering wave condition. So it means if we know the S1, S0, S1, 2, 3, and then we, of course, they are corresponding with the fusion as maybe X1, X2, X3, X2, X3. So this is the, the advantage. If we know they're reflected, and then we can calculate the transmission. So that's why here, if we know the coefficient cross-section, and then of course, automatically we can calculate the quasi-elastic cross-section. So this is the But before I give you the result of our calculation, I will tell you the other advantage of when we measure the fusion cross-section. That is, we plot the cross-section in different way, and which we call it fusion barrier distribution. That is the second derivative of the multiply of energy and cross-section. And this is, this equation or this concept is very sensitive to the detail of nuclear structure, because you know the structure of the nuclei and nucleus, they will be spherical or can the form. The form means looks like pumpkins. Kind of spherical is a ball, but the form looks like pumpkin. And this is by including the channel coupling in our when we solve the coupled channels equation, so we can now I will give you for example see, so this is the difference here. I mean, this is a potential model calculation. When we include the rotational coupling in our calculation by solve the coupled channels equation, now we can explain the experimental data very well. So the red line is the coupled channels equation by including the rotational coupling, hexadecapole and quadrupole excitation of the samarium 154. We know the samarium 154 is an example of nuclei which have the forms shape. And then this is the concept of barrier distribution. This solid circle is experimental data, and the red line is calculated theoretically. So here we know that coupled channels equation can explain the experimental data very well. And then one of the advantages of the fusion barrier distribution, you know, I mean, in nuclear reaction community, the shape of the nuclei, they measure by using the Coulomb excitation. But now in our, in our community, by using the experimental data of fusion cross-section, we can also determine the shape of the nuclei. The example is here. So if we change the, the sign of the beta 4, it's beta 4, the shape of the nuclei, the shape of fusion barrier distribution is totally different. Even the experimental data of fusion cross-section can be, can be explained very well, but the calculated fusion barrier distribution is totally different. So the red line and the blue line. So the blue line can experimental data explain the experimental data very well, but the red line is slightly different with the experimental data. It means this is for oxygen 16 and samarium 154, and the right side is oxygen 16 plus tungsten on 186. It means here from the data of the fusion cross-section, we can also extract the, we can also determine the shape of the nucleus. So that means fusion is a quantum tunneling microscope for nuclei. And this is also the one of the example, when we try to determine the shape of the nuclei, the nucleus, this paper is already published in Physical Review 2010, I guess, 12 years ago. We use the concept of barrier distribution to determine the shape of the nuclei. We use the experimental data of germanium 74 plus germanium 74. And also the concept of coupled channel method we can apply to the astrophysics. Here we calculate the cross-section and astrophysical X factor. And then our calculation is very good agreement with the experimental data. And then this is data is already been published 2015 in Physical Review C. One of my student in the at the University of Malaya, Kuala Lumpur. Now, what about quasi-elastic? As I explained before, the quasi-elastic and fusion is complementary each other. So if we know fusion, we can also know the quasi-elastic. we know also the quasi-elastic scattering. So they are related to each other. So it means the fusion barrier distribution and then quasi-elastic barrier distribution should have the same shape, because they are the two processes complementary each other. I will give you the result, but about this fact. So this is the our result that fusion barrier distribution and the quasi-elastic barrier distribution is very similar to each other. It's given by Hagino in Physical Review Set 2004, and then we also give the result that the fusion barrier distribution and quasi-barrier distribution is complementary to each other, and it's we prove it 4 years later, 2008. And then this is also the couple channel calculation for quasi-elastic barrier distribution. So we can explain the experimental data very well for the quasi-elastic quasi-elastic scattering cross section. I mean, this is with what I show you today is the result of our calculation to explain the experimental data for fusion cross section as well as for quasi-elastic cross section. This is for oxygen 16 plus samarium 144. Samarium 144 is known as the nucleus, which have the spherical shape. And then we also try to explain the experimental data for very heavy system, that is CR 54 plus lead 208. If we sum this one, we will have the nuclei with mass 264. This is very heavy nuclei. And then, you know, here by including the channel coupling in our calculation, we can explain the experimental data of fusion quasi-elastic cross section as well as the quasi-elastic barrier distribution. And then we published also in 2008. And then we calculate either by including more channel. Our calculation still explain the experimental data very well. This is we published in 2006. And now, but the problem of the fusion and quasi-elastic scattering is here, detail of the sensitive to the only to the surface region. That means surface region is only determined by this A parameter or surface diffuseness parameter. The problem in our fusion community and quasi-elastic scattering is the difference between A. In fusion, sometimes we need the very large A, is around 1.0 femtometer, but for quasi-elastic scattering, they only need the surface diffuseness around 0.6 femtometer. I will show you the facts. Okay, and this is the fact. Our calculation also show that the quasi-elastic scattering needs the very small surface diffuseness parameter, that is around 0.6 femtometer. And then very recently, we try also to calculate using the experimental data of neon 20 plus nickel 58. Because we have to calculate do the couple channel calculation with various A from 0.2 to 1.0, but because the calculation is took very long time, and then we just only take a few A, and then what we have done is by using this data 0.45 to until 1.0 FN, and then we do the extrapolation, and then we try to find the chi-square between the calculation and the experimental data. So we find we search the very small chi-square, and then we get the surface diffusion parameter for this system, and then for the quasi-elastic scattering between neon 20 and nickel 58 is around 0.8. So it means it's almost the same with the fact what we have, obtained by others researchers. Of course, we have to make many study about this to confirm why the difference between the surface diffuseness parameter of fusion and quasi-elastic scattering. And then this is we prove again that the quasi-elastic scattering and fusion have the similar fusion barrier distribution between quasi-elastic and quasi-elastic and fusion reaction, and we already published in 2019. Of course, many things. I mean, many efforts we have to do to explain the difference between the experimental data and the theoretical calculation. Also, the many facts that we have found in our study, especially the difference between surface diffuseness parameter of fusion and quasi-elastic scattering. Until now, the study on that problem, of course, many researchers try to explain this. So I guess this is the summary of my talk today. It means by using the coupled channels method, we can explain the experimental data of fusion and quasi-elastic scattering. So now the structure of the nuclei, we can use the concept of fusion barrier distribution as well as the quasi-elastic barrier distribution. Of course, many effort we still have to do to explain the experimental data. Maybe they will. I mean, the experimentalists and we are theorists. We also have to work together to collaborate to explain many experimental data will come out in the near future. Thank you very much, and I will. And I'm so sorry if many my presentation you see too many equation or something, but this is at least if we have friends, we can discuss about this, and then we can collaborate each other to know about the nuclear reaction study of the nuclear reaction. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Okay. So this is my collaborator from, of course, Tohoku University, Japan Atomic Energy Agency, Australian National University, Asyut University Egypt, University of Malaya, Kuala Lumpur, and International Islamic University of Malaya. Thank you very much. And then can I stop my slide? So okay. Thank you.
Okay, thank you, Professor Jamrun, for the inspiring presentation. Even though very much equation in this presentation, I believe participants will give questions. So please prepare your questions, and then the second presenter, you can send your question in column chat or raise hand. Okay, ladies and gentlemen, the next presenter is Professor Marcus Diantoro. As we mentioned before, he is head of Institute for Research and Community Services, or Kepala LPPM, Universitas Negeri Malang. He will talk about challenge and prospect of photo supercapacitor, dye sensitized laser blocking, and active layers modification of their photo supercapacitor performance. Professor Marcus, the next 40 minutes are for you, please.
Thank you, Prof. Risa. Could you hear my voice?
Okay.
Okay. Okay, thank you very much. Very good morning, everybody. Thank you very much, Mr. Chairman, Prof. Nurani, and as well as Pak Arisa Suryana, my best friend as well, about maybe 20,000 years ago. Mr. Ceremony, Master of Ceremony, also all of the participants, as well as of the honorable presenters in this ICOPIA 2022. Okay, after inspection of the first presenters, would be maybe it's not my field as well. There's too many equation, yeah, Pak. Now I would like to present several of my current research and my groups. What the title is Challenge and Prospects of Photo Supercapacitors, and abbreviated by PSC. Of course, there are many types of photo supercapacitors. Now, in my group, focus on DSSC. In this case, in this occasion, we would like to express, present, focus on blocking and active layers modification on its performance. This is my group, several of my group. I came from Department of Physics, Faculty of Mathematics and Natural Sciences, and we have one of PUE, Center of Advanced Material for Renewable Energy, will be already given the degree from the ministry last year. Okay, this is one of the main gate of Universitas Negeri Malang. When you come to Universitas Negeri Malang, normally this is the main gate. You will see the Geraha Rektorat, and my department is actually somewhere here, just behind this buildings block. Okay, this is the outline. Maybe not many equation as the previous plenary session. Now I would like to present several short background and what is supercapacitors, and then the components of supercapacitors, preparation and method. This is not summarized, but is specific one of our group of the current and current progress. And then we propose some prospects. Of course, we have problems and challenges following the title. Okay. Around 90% of the world's energy consumption is now based on the fossil. But according to PVPS 2016, the fossil fuels around the world will be reduced and could be survive maybe next 40 to 60 years last. Now, researchers now growing to focus on the research building to the supercapacitors or maybe battery. Yeah, and the solar cell is one of the challenging for the market. Of course, in the markets already provided by several industries, but according to many aspects, we would like to promote, to search, to gain some materials and also some prospects of the supercapacitors as well as the battery for storage. And the solar cells, one of the converting energy, harvesting energy from the world. Now, in this case, we would like to combine these two different devices, solar cell as well as supercapacitor, to be as one of the device, what we call it photo supercapacitors or solar supercapacitor. The solar cells, of course, to promote the harvesting energy and self-charging, we would like to minimize the volume of the devices. That's why we combine both of them in one device. Okay. Now, actually, people and some researchers promote there are different mode. Yeah, what we call it mode 1, mode 2, and mode 3. The convention is, in this case, it's a DSSC or solar cells, and the storage maybe we could combine even standalone of the battery or maybe standalone of the supercapacitor. But we could also combine in the storage both of the battery and supercapacitors, what we call it supercapacitor in one devices. This is actually both of the solar cells and the storage is different devices. If we would like to install the lamp of the solar cell in the road, we need the solar cell itself and the storage itself. different. That is different. In the second mode, both of the conversion system or device, what we call in this case is a solar cell, and the storage, or maybe battery, or maybe you can use a supercapacitor for the fast charging. This actually different case, different devices, but compacted in one module. This is what we call it mode 2. Mode 2. And then the last one is mode 3. Both of them, the conversion device as well as storage devices. In this case, we use DSSC for converting energy from the sun to the electric, and then if we do not use the energy on the load, we store direct to the storage. We can use the battery as well as for supercapacitors. This is what we call mode 3. The mode 3 is what is now being discussed in my presentation. But actually now people also promote this is not devices, but actually one device came from the one system of materials. Yeah, this is a new proposals, what we call it mode 4, but not presented in this one. Okay, what we are doing now is combining and using this mode to obtain the dual function device integrating for solar cell as well as supercapacitors. And we would like to have self-powered electrochemical energy storage from this directly from the sun. We need no other electrical from PLNs, like for example, yeah. And then we would like to obtain the integrated photo superchargeables for supercapacitor from electrode sharing. So for this case, we have to have a common gate or common substrate for combining these two. Okay. The sandwich should be like this. One is the photovoltaic, yeah, or PC or PV, or we can use here as a solar cell for PV parts, this block. And then a storage part we can use here. This is the battery type or supercapacitor type. The counter electrode, electrolyte and dielectric materials. Now we have a common electrode to be used for both of the for the storage part, supercapacitor, as well as for the PV or solar cells. Now the construction configuration could be like this. Yeah, this is the common. This one, the common electrodes. Yeah, this is the PV part. This is storage parts. Or maybe we have later I've screened for you to. We do not use this kind. Yeah, we have just flat. Okay, the component of supercapacitors we talked previously. In this case, we have PV parts or solar cell parts, and then we have storage parts. In this case, we use supercapacitors. Now we have three gates, actually. AB is the gate for measuring the system of solar cells. And the BC standalone for the supercapacitors. But when AC is just connected, this is we directly connect from the energy harvesting from the solar cells directly to the storage parts, because we have common here. Okay. In our case, we have PT as a counter electrode, and we use iodide for the electrolyte, and we use the combination between titanium dioxide and 719 for photoanode. We put some spacer or saline. We use also the modification of the blocking layer here. Actually, the basic is the titanium dioxide, but different density, different conductivity, so it would be a reflective one. This is FTO, and then this is this part, yeah, dye and titanium dioxide. In this case, we would like to present the modification of these parts, the blocking layers and the active layers. So actually, the supercapacitor is the standard in our group. Yeah, this kind. We use this is aluminum, and this is also the aluminum. Sometimes we use also copper. Okay, the detail is the next slide. So the detail of the DSSC or as a photovoltaic part is when the solar light came from this side, and then we have a compact film. We call it, this is a blocking layer, actually the same titanium dioxide, but different density, also different electric conductivity. So it can reflect it and then back to the light. So by using the titanium dioxide and the dye, converting using the electrolyte, converting the sun energy as electric energy. So by this electric energy producing by the DSSC, it could be directly used as a energy source. But of course, when in the daylight, it is not necessary to use directly. So we can start in the next part. Okay, the photoanode is transparent conductive substrate. We use FTO in this case, and the semiconductors we use titanium dioxide. Of course, you can choose also zinc oxide as well as another semiconductor oxides. And the dye we use N719. Okay, what we would like to improve is the improving the SSC part, because this is the fundamental part in the PSC or photo supercapacitors. Because if we have storage with very high capacitance or very capacity, but if we convert only very small energy from the sun, of course we can only store very small as well. It is also depends on the efficiency, not only efficiency of the solar cell convention, but we now promote as well this efficiency total from the solar cell as well as the efficiency from the storaging from the energy conversion of from the sun to electric, and then converting to the supercapacitors. This is image of the SEM from our group. This is the blocking layer, very thin, 0.243, and then the mesoporous layer. It is actually the same from the base of the titanium dioxide, but the different porosity. And then the reflective layer, which we call it, both of them is active layers. Now this, if we have already prepared this one, we put the dye in this part, and then later we put the titanium for the counter electrode. The thickness is, this is a typical thickness of our group of the GSSC. Okay, now we come to the second part of the photo supercapacitor of PSC. We call it supercapacitor parts. The capacitors, the supercapacitors is actually based on the capacitors, but now the efficiency, the capacity is very much different, about 10,000 times compared to the conventional capacitors. So that's why we call it as supercapacitors. Okay, we have two different electrodes. Yeah, if we have a symmetry system, it means the cathode and anode is the same. If we have both electrode are different, so we call it asymmetric system. So the electrode could be different. The anode part and cathode part is different. So in this case, if we have a symmetric system, so the electrode for cathode as well as for the anode is the same, separated by supercapacitors, separators, and in between of them, we have an active material based on the now in this case we propose based on our carbon natural carbon sources. Okay, what we need is the active material with high surface area, also conductivity, as well as he or CH could be a good capacity or dielectric material. So we have to make a combination of that. Not so high capacitance, but we need to modify as a dynamic one. If we choose the material from very high dielectric materials, so we will act as a capacitor, not supercapacitor, because this is a static one. So that's why we could combine with several materials with high surface area and the conductivity around the not so conductive as conductors, but in between of conductive and dielectric one. So the conductivity and electron mobility, one of parameters we could combine, we choose which one is the best. Okay, the electrode is functioned to conduct electric current, good electrochemical stability, and good ionic conductivity as well. So in this case, we can use the electrolyte, any other type of electrolyte. Normally, people for experimental use this non-solid because it's very cheap, yeah, inexpensive one. But normally for the long term of the use, people now use a solid electrolyte. Okay, the component of supercapacitors is the conductive material, active materials, and the binder. Because normally when we have no good addition between the material, active material, and conductive material to the substrates, when we put a current or voltage on those devices, normally the active material and conductive material will be taken away from the system. So that's why we need another material, what we call it the binder. Many binders available in the market, so we can also modify for the binder as well, not only the active and conductive material. Normally we use carbon black materials, and then for the active material we use activated carbon materials. Actually both are the same, yeah, the carbon one, but both of them is different density and different capacity, as well as different electric conductivity. So the activated carbon could be also came from the carbon black materials. But of course, we use another active material from the metal oxides. Normally, we use metal oxide, let's say from the manganese oxides, or maybe from the calcium mangan oxides. It's also normally used for the battery. Okay, this is the components of supercapacitors. So to prepare of the photo supercapacitor, we have to prepare of the component, the supercapacitor as well as for the solar cells. So this is part one. We call it adhesive fabrication. In this case, we have FTO for the substrates, as well as for the transparent material, to allow the sunlight to come into the active layer. And then deposited the blocking layer, very thin and dense, we can use from the market available. And then the next step is deposit the active layer, and then the reflective layer, and then post-treatment. Normally we use several degrees of Celsius, And then it is also possible to absorb any other water or air when when we do not use it. This is the best one actually. But normally people in Indonesia, since in the laboratory we could not have any other material and very clean room vacuum. So normally we just put directly from post-treatment temperature treatment go to the dye immersion. This is actually the most important part. If we have a very high density of water in our air, it could affect on our photosupercapacitor as well as the DSSC part of the efficiency. So this is the fabrication of DSSC. This FGO from this part, and then TiO2, and this is the dye. And then we put next for the electrolyte. And then this is the counter electrodes, PT1. Then from this case, for DSSC part, we firstly check correct by IV, semi-SLD, UVs, and IV for solar cells. Okay, next part is photo supercapacitor fabrication, and then the part later with integration of PSG. This is the supercapacitors part. We have to prepare composite of activated carbon, carbon black. This is what we call it. What in our previous one is binder one. Yeah. Okay. Continue then. We deposited the base. The slurry is also possible. Activated carbon, CBSBR on aluminum foil, and then to confirm that we will characterize with SID and SEM, and then combine together with the separators, both sides. We can see here that aluminum foil as ACCB is the same part with the other side of electrode. So we call it, this is the symmetry system. Okay, of course you can use asymmetric one or the hybrid one with the higher, what we call it, with high capacity and energy density as well as power density. So in this case, we just prepare the symmetric one, and then the next part is the combining between this DSSC part, this one, and the supercapacitor part. We use the common aluminum foil. Yeah, this is the common substrate, the common electrode in our system. Okay, this looks very simple, yeah. This is photo supercapacitors. This is this part, the supercapacitor one, and this is the DSSC part. Okay, this is the detail one. Maybe I can skip this one for you. This is image of the procedures what we have prepared and summarized in our previous parts. Yeah, it's actually the same. So here we have one compact of the supercapacitor system. Okay, now back to the system. What we call it, this one is symmetry of the supercapacitors, and this is DSSC, but the configuration of the PSC is now, we call it series, because we use the same common as like this way. Yeah, actually we have prepared as well for the parallel configuration. It means this is in the top one and this on vice versa like this. So we have actually two gates, but we have actually three combination gates: AB, BC, and AC gate contact. So for the AB gate, we have to have the performance of the DSSC. If we have a look for the contact, the BC is to obtain the properties or the characteristic of the supercapacitors. When the contact A to C, of course, we have to use diode, yeah, to not allow back current flow. So we have directly, if we put the sun this direction and then convert here and then direct A to C get contacted, it means the energy conversion from the sun will be converted, stored in the supercapacitor parts. Okay, this is several equipment what we use as powder X-ray diffractometer, FTIR, SEM-EDX, and then this is Cambridge and newer PTS. This is for this is similar, but it is for more complex one. We have to use as ACE and charge-discharge for our system. And then UV-Vis and the IV sun simulator for the solar cells. Okay, now we would like to present our small current research. The first system is PIC based on FTO TiO2 titanium dioxide and 719 and AC PC carbon black and activated carbon. This is our system. This is the curve of voltage and current density. We should cut from the zero. Yeah, normally we can go through the negative part. Of course, the physical meaning is on this curve from the positive part. Okay, from this one, it means we can use this system standalone could be used as a source for light emitting diode source, because it's already around 0.7. Yeah, but if you use this as a series, we can combine series as well as the parallel. We can combine the current as well as the voltage for the performance of DSSC for directly to the load, let's say for the lamp. Okay, this is for the variation of the sample according to the duration of the immersion of the dye to the TSSC part. So this VOZ, this one, the open current circuit voltage, and then GST, this one, and then fill factors. This is normally people also would like to know, we would like to increase the fill factor. Normally when the fill factors increase, the conversion or the efficiency also increase. But this is sometimes not only according to the fill factor, but also of course according to depends on the VOZ and then GSC. We have looked in this case that increasing the immersion duration, it means the amount of the dye is also increased. We will have a look at I'm sorry, this the conversion of the efficiency. We obtained the optimum is about 22 hours. This is also happened in different systems from the literature. Normally around 22 to 16 to 24 hours. It means one full day. Okay, this is the absorbance of the samples from the 7 hours, 12 till 27 hours. We have looked here. There are two peaks, peak one and peak two. This is came from the titanium dioxide, and this one came from the dye. Okay. Here, another photo response of the same system with different amounts of the or different duration of the immersion of the dye. We put here the gate. It means the same gate of the AB, yeah, from the FTO and then the contact of the platinum. Okay, this is on off lights, and then this off of the lights. Actually, this quite small gradation of the voltage, but based on this, we can have a look as well. But for this, the same as the previous result, that 22nd hours is the best samples in this case as well. Of course, we can use this data to be normalized and to obtain several physical parameters. And the last one is the ACE data analyzed by the Nikis plot. This is the equivalent equivalent circuits of our system. Okay, this is the semicircle from the Nikis plot. And then we have fitted, we have already fitted for this three system, 7, 22, and 27. 22nd hours is also the best one. Okay, this the other system. The retention is around 98% until 50 cycles. So it means quite okay, yeah, for the operation. Okay, this is a photo supercapacitor of the system of the DSST combined with the supercapacitor. We call the PSC, photo supercapacitor. The photo response of A, B gate for DSST, and PC for the supercapacitors, and to store is A to C. Yeah. Okay. This is we have two different configurations. This is what we call it parallel configuration. This is this common ground or common substrate. Yeah, and in this case we call it a series configuration. This is the common ground or common substrate. In this case, we have also different efficiency of the total storage. Yeah, one is conversion from the DSSC and multiplied by the storage efficiency, what we call it overall or the total efficiency. Okay, it looks that the parallel, yeah, is a higher voltage, and the series, this one, with still lag compared to the parallel one. Okay, this is the system. Yeah. Previously, we have modified with the amounts of the N719. Now we would like to give rise to maybe a small summary of the photoanode modification. One is the modification of thickness of blocking layer, and the other one is the thickness of the active layer. Okay, maybe we should come quickly, yeah. Okay, the thickness of the system we promote and drive using the different mesh. The lower mesh means higher size of the particle, so we can go also thick, the thickness also higher. It means if we use the higher mesh, we will have the more thin layer. Okay, this is the result of the X-ray diffractometers. This is the intensity and 2 theta. Of course, we clearly seen here from the different thickness or different type of the mesh. We have looked here that all of the peak is identified by the titanium dioxide. The crystallinity is decreased when we use a higher mesh. The crystal size, as we expect, that when we use the lower mesh, we will have a higher crystal system as well as the amounts of titanium dioxides. As we expected, this is the distribution of the thickness, yeah, using same image. And then this is the cross section of the samples, T14, 16, 17, 90, and 120. Of course, we have a look here that this is a 12 till 90, 92, around 70. Yeah. Okay, this is the result of the thickness plotted compared to the mass type. So it looks like that the increase of the mass is decreasing of the thickness, or vice versa. Yeah, this is the energy gap using touch plot analysis. We have two different gap energy. This is from titanium dioxide around 3 point something, and then here 2 or 1 point something is the die of gap energy. Okay, here is the DSCC part of the system of second part with the different thickness of blocking layer is a little bit higher compared to the previous one with the various of the die immersion period. This is not only for VOC, but also for GC. Yeah, this is from the different references. The thickness is also somehow similar, yeah. But from the type of our system, type of method system is this is now the driven of the thickness of our system of blocking layer. But if we see from the system here, we look at the thickness of the solar cell with T16 is looks okay, but the PCE for full fill factors, VOC and GC is somewhat anomaly. Till now, we could not explain due to a lack of our data of the sample. But if we discard this sample, we can have this type of trends, not only for the GC, VOC, FF, but as well as the efficiency. It means the high efficiency is obtained by the thickness, higher thickness, higher crystallinity, as well as high porosity. Okay, yeah, this is a comparison between blocking layer as well as the without blocking layer. The blocking layer with blocking layer is higher. Yeah. Next, this is the similar system we evaluate, compare it with the on and off of a light. Yeah, this is on of the light. This is off of the light of the sun from the solar simulator. But it looks flat, but actually something somehow of decreasing this flat one. Similar of the previous result, the PL1 to PL4, we have also something around what we call it anomaly, because normally in the literature is follow of our system from 1.7 till 4 point something or 7. Yeah, it means with higher blocking layer, higher density, we will achieve for the efficiency or photo capacity efficiency. Yeah, this is the best one actually for the best of our results is compared to other result of the literature until now. This is also supercapacitors parts of the second system. Yeah, this is a CB and AC. This is specific capacity and energy density. This is around 60 watt-hour per kilogram. This is close to the battery one. When we compare to the battery, around 8 80 to 120. So when we what we call it here as a supercapacity, yeah, because the capacitance as well as the energy density as well as the power density is close to the battery, but the system is actually supercapacitor, so we call it supercapacity. Okay, this is a experiment on off of the system. In this case, we use the best one. The thickness is the highest one. This is the lights on. We have some delay, and then light off. We have some delay as well. This is also depends on the system. Yeah, the very steep is very base, of course. But in this case, not one. On the vice versa, we need like some delay. It means after the off of the stopping of the lights, the system can still some mechanism to convert from the sun inside the active layer to the electric one. Okay, this is photo supercapacitors, this one, and it's the standalone of the SSD. It means when before combining in PSC is still better compared to after combining of as a PSC of the DSSC. But this is the standard of the DSSC, this one, and then this is after combining in the system of PSC, photo supercapacitors. The efficiency of the charge transfer from DSSC is around 85%. It's a good one. Okay, this is a plot of the current and elapsed time from the on-off experiment of all of the system T48 till T120. It means T48 of the higher thickness is still the best one. This is a second modification of the active layers of the blocking layer. Okay, the parent is also, this is the best one, still the best one. Okay, next one is some physical parameters of the thickness. It goes like this, but this is what we call it anomaly, or maybe we have to look further how T61 is decreased like this. Even all is this trend. This is came from the absorbance. This is the position of the peak of the wavelength, and there's a PCA, the energy conversion or efficiency. Put is the best one, but in between, why this decrease? Still to have a look why this decrease. Okay. Next, this is the different thickness with the blocking system of the second system of blocking layer. This is blocking layer 1, PL2 till PL4. The best ones still obtained by the 8.19. Yeah, this is the best one. Compare even to other literature till now of the DSSC system. Okay, some prospect and also challenge of our system now. When we reduce of the solar cell as well as the normal or standalone supercapacitor, now we can combine in one system what we call it photo supercapacitors. But of course, when we expose this system in under the sun, the system may be degraded. Why? Yeah, this is a big challenge because the temperature, the higher temperature will also decrease the performance of the supercapacitor part, this part. But of course, we can reduce not only the price, but also the volume, as well as another possible connectors for using photo supercapacitors. So the challenge is how to increase the total efficiency, not only single efficiency convention of the DSSC part, but also after the conversion, storing energy to the battery or the supercapacitor should be also high as efficiency. If we use this system not in the line of the PLN, so we can not only modify the system, we can install the system in many other building or any other occasion everywhere, as well as long as you or we have the sunlight. The light is, of course, not only came from the sun. We can obtain from any other sources as well as any light. We can convert the light of photon to electric energy. But of course, the higher intensity of the light will produce a high efficiency of the conversion of this part. Well, why we need of the equatorial territorial like Indonesia? This is one of the good reason why we should focus our research on this system, yeah, photo supercapacitors. Okay, the problems is still lack of poor performance of the level of the SSC. Of course, we can now change not the SSC, but we can use also for the new type of solar cell, like modification of the silicon base or modification of the oxide base or the modification of the flexible, as well as new type, the fourth generation. For the battery or the system of the not the PV, but for the storage system, we can modify not only for the supercapacitor, but also we can combine between the battery as well as the supercapacitor in one system, not only as two systems combined in one, like our system of photo supercapacitors. I think this all of our presentation. I hope all audience can read of the listen of our presentation, and we can go further together for this field of photo supercapacitor, even the standalone of supercapacitors or standalone of TSSC or solar cell, or this of combination. Thank you very much. Back to the moderator. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Professor Markus Diantoro, for the interesting presentation. Okay, ladies and gentlemen, Bapak dan Ibu, now we come to the question and answers sessions. Okay, I will invite 4 questions. You can write in a column chat or raise hand, and then please mention your name and to whom your question is addressed, either Prof. Jamrun or Prof. Markus. Please.
Sir, I have questions, sir.
Okay, Ibu Sri Mulijani. Okay, yeah. Please.
Okay, thank you very much for moderator, Dr. Risa Suryana. I'm Sri Mulijani from Department of Chemistry, IPB University, Bogor. And then my question is addressed to Professor Markus Diantoro. It was very interesting presentation, sir. And then also topic. And it's a very good topic because I'm also working in that DSHA or topic also. And then my question is, okay, and then as you mentioned in the morphology of the substrate of dye, you have also saw what is the morphology by scanning electron microscope. And then my question is how to get the and then how to measure the thick, I mean, for the that one, the substrate, titanium oxide, and then also the dye. Is it? That's one question. And then another one is the what kind of the dye did you use for your research for the SHA? Is it natural dye or synthetic dye? And then the third one, I have many questions, sir. And then I would like to get the collaboration with you in this topic only. This is my pleasure if I get collaboration with you in this topic. And then the third one, and then you have also mentioned that there is one what photo capacitor for this essay also. Then you only use one FDO only, flat. You mentioned it A, B, C. Am I right? Okay. A, B, and C. And then you do contact it with the A and C by what I mean, that's outer electricity. Yeah. And then you only use one FTO. So can you just please explain me briefly? I mean, that's I still I want to get more explanation. Thank you very much for Dr. Risa. And that's all my question only. Thank you, thank you.
Okay, thank you, Ibu Sri Mulijani. Okay, I'm waiting for one questions because Ibu Sri Mulyani has three questions. Please. Okay, I have one question for Professor Jamrun. Okay, I have one question because you talk about couple channel formalism. Yeah, couple channel formalism for fusion reaction and quasi-elastic scattering. So you saw many equations. So I think because your data always compare with experimental data. So my question is, what kind experimental data you did by yourself, or you take in secondary data? Okay, just one question. Okay, please. I think the first one for Professor Marcus Diantoro to answer Ibu Sri Mulyani.
Yeah, thank you, Parisa. And thank you for the question, Bu Sri Mulyani. Very interesting. Yeah, the question also very good. It means the answer is not so easy. Okay, Bu Sri Mulyani talking about the dye, it is natural or synthetic one. This is how to measure the substrate, the Al2 and the dye as well. And the last one is about the, we have promote three gates, three different gates, A, B, C. But normally we use normal FTO. How we can use those FTO for both sides? Okay. Okay. Yeah. The first question, actually, I think I would. Can I share, Parisa?
Okay.
Okay, back to the presentation. I think this. Okay. Hope this will help you, Pusri. Of course, for the detail, we can discuss later after the presentation.
Yes.
For
Thank
the
you.
collaboration, of course, in this ICOPIA is a good occasion for us to make a collaboration, as Pak Risa presented previously. Okay, we will contact later, Pusri. Yeah, thank you.
Thank you so much.
For the offering. Yeah, I think in our case, we have this system. This is, of course, the illustration to obtain what is the titanium dioxide as well as the dye is inside. Of course, we cannot use only one characterization to obtain it is already there or not the dye. We have used the FTIR as well as UVVs. The band gap is already preset of those two. It means one from the titanium dioxide and the other one from the dye. The same image we cannot obtain from the dye. Yeah, of course. Even for titanium dioxide, we can obtain the information. Are there any titanium dioxide as in our system? Yes, but we have to complementary inspection using EDX. We have a mapping of our window of our samples. If there are outside oxygen as well as a titanium on the system, it means our titanium dioxide also there. The second characterization, the other characterization is by X-ray diffractometer. When we use X-ray diffractometer, of course we can only obtain the information from the crystalline parts. Fortunately, our titanium dioxide is crystalline. Of course, not our dye. So that's why we can assure that our system is already there. Titanium dioxide, blocking layer is also there. But what is kind of ambiguous of not so expert researcher? Normally, our students is now ambiguous between the titanium dioxide of the active layer with the blocking layer. Actually, both of them came from the same system. It means from the titanium dioxide. But the blocking layer, somewhere here, is very, very thin and very dense. The density is different. So we have to inspect not only from the top view, we have to inspect also from the cross-section side view. This is for the first one. The second question is related to the dye. Yeah, in this case we just bought from from the market. We use the synthetic one, the N719 book. Yeah. Also, although we have actually provide many natural dye, but up to now the natural dye provided by our group is still lower than the synthetic of 719. Okay, the third one is the gates. Yeah, that's a good question. Of course, the common ground of the common substrate, we have to use both sides of conductive. So that's why when we use the FTO, we have to choose not the common FTO. Normally, common FTO is just one side conducting. So in this case, we use two sides conducting, double sides conducting of FTO, the top and the lower parts. So this this P is actually two different sides is conductive of FTO, this part and the other side's parts. Of course, we can replace this FTO by using let's say very thin substrate like aluminum. Yeah, because in this case we actually we do not necessarily use the transparent one. Yeah, we can use aluminum or platinum, but of course platinum is very expensive. Normally we can replace this FTO by using a very thin foil of conductors. I think hope fulfill of Bu Sri Mulyani questions. Thank you.
Okay. Thank you very much, Professor. But I have experience in the. I just put it in sandwich type. I mean, both up and bottom. We put in the same FTO. I use ITO, not FTO. But we do like sandwich. So we put like that only. But that's very nice, very new for me. You use that aluminum, the thin aluminum, and then you use also the platinum part. Thank you very much. Thank you very much for your
Welcome.
kind answering. And then if you don't mind, let me get your mobile number, please. Thank you.
Sure, you can contact Pak Risa, ya.
Oh, Pak Risa, Dr. Risa,
Already have
thank you
my-
so much. Okay,
Okay.
thank you.
Okay, thank you, Bu Sri Mulyani. Okay, you can continue discuss with Professor Markus Diantoro through email or WhatsApp, right? Okay. Okay, the next question, please, Professor Jamrun. Unmute. Unmute. Okay.
Of course, I'm a theorist, so I just working in front of the computer. But the data, of course, is from my collaborators from ANU or from Europe or from India. And then when sometimes we visit them, how to measure the how they did the experiment. We didn't do the I didn't do the the experiment for get the data, but I get the data from the primary source, not secondary source. Okay, thank you.
Okay, thank you. Okay, the next question. I'm sorry, Prof. Jamrun. Okay, in your presentations, you saw about oxygen 16 and samarium 154, ya, atau ya. I want to know why you always choose oxygen 16 and samarium 154.
Actually, we have many data. I just saw this. Because the experimental data and the calculation is, without by not including the another effect, the difference between experimental data and the calculation is totally different. That's why I showed here. Actually, I have many data, around maybe 30 or 40 data. So I just show you how to impress you that our calculation can reproduce the experimental data. That's all. Thank you.
Okay, thank you, Prof. Jamrun. Okay, participants, any questions? Please write in column chat or raise hand. Okay, I have also I have a question for Professor Markus. Because you integrated or combine between harvesting energy and then storage energy, which means use dye-sensitized solar cell and then supercapacitor. So you made 3 gate A, B, C. I think I'd like to ask about contact, material contact, to measure between AB, AC, or BC, because I think the contact also affects measurements value. What do you think, Prof. Markus?
Could I reply directly, Pak Rizal?
Okay. 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 I would like to. I have a question about the contact material.
Yeah. Okay.
Yeah, contact material to measure get A, B, AC, or BC.
Yeah. Yeah. Actually, the contact is actually the substrate itself. Yeah. Let's say for FTO, the DSCC parts. Yeah, because there's also there is a conductive parts, a conductive side. So we use this side to contact one. The most challenging is what we have see from the Bu Sri Mulyani question is the P contact. The P contact is also could be used using FTO double sides, conductive double sides. But of course, it's very challenging because because these substrates or FTO double sides also can be used as a conductive contact for the DSCC as well as the conductive contact of supercapacitors. So normally, when we do not have any double side FTO, we can replace this by the normally, yeah, for the experimental problems, technical. So we replace this by using aluminum foil. So very cheap, but it can still be used as a contact to measure not only for the DSSC part, but also for the supercapacitor parts. This also happen when we would like to contact store directly from the DSSC conversion from the sun, the electric energy conversion from the sun. So we can directly contact E to C with some additional electronics one, at least the diode. When we not put the diode, sometimes if we have already full of the capacity of the supercapacitor, they can back direct, to the DSSC parts. So that's why we put some electronic devices. Normally, we can also use a very simple one with the diode, Pak Riza.
Okay, thank you for your explanations. Okay. Bapak Ibu, ladies and gentlemen, any questions? Okay, please raise hand or write in a chat column. Okay, no questions. Okay, ladies and gentlemen, Bapak dan Ibu, yeah, I believe you still questions, but time is over. I think 10:15. Yeah, so you can talk or contact directly to Professor Markus Diantoro or Professor Muhammad Jamrun through WhatsApp or through by email. For WhatsApp or email, you can you can contact me, and I permit you your Prof Markus or Prof Jamrun to give WhatsApp number. Okay. Okay. Thank you.
Sure, Pak Rusa. It's okay.
Okay. Okay. Once
Thank you very
again,
much.
please give applause to both speakers, Professor Muhammad Jamrun and Professor Markus Diantoro. Thank you very much. Hontoni arigato gozaimasu. And now I return the next session to Master Ceremony. Please.
Okay, thank you, Mr. Rizal Suryana, and thank you for our extraordinary speakers, Professor Dr. Zamrun and Professor Dr. Markus Diantoro. And before we continue to the next plenary, I'm going to welcome you, our next moderator, Dr. Ahmad Marzuki, an assistant professor from Physics Department, Universitas 11 Maret, to carry this session. But before, let me check you, Mr. Ahmad, could you hear me?
Yes.
Okay, then thank you, Mr. Ahmad. Okay, Dr. Ahmad Marzuki, time is yours.
Okay, Thank you very much, Mrs. Haya. Assalamualaikum warahmatullahi wabarakatuh.
Assalamualaikum warahmatullahi wabarakatuh.
Okay. Good morning, everyone. I hope you are all very well today, this morning. Yeah. Okay. I'm Ahmad Marjuge, as introduced by Mrs. Haya, the MC for this morning sessions. So I will moderate this second plenary sessions. We have two, I think, scholar now. So this morning already joined with us two scholars. First is Professor Dr. Idris Kabalji. Assalamualaikum, Prof.
Alaikum salam, Professor Ahmad Marzeki. Good morning.
How are you, Prof? Are you okay?
Thank you very much. Everything is fine.
Good.
And greetings to all participants and chairman, organizer from Turkey. In the morning, early hours here. So wake up early and early join to the conference.
It must be very early morning at this time, so Prof, at your home.
Yeah, it's okay.
Okay, Prof. Okay, Prof. And the second scholar, Dr. Francis Klex. Good morning, Dr. Francis Klex. Good morning, Dr. Francis Klex. Are you hear me? Okay. Dr. Francis Klex will deliver his talk after Professor Dr. Kabalji, so it's okay. So I will introduce him later after finish with the talk by delivered by Professor Dr. Kabalji. Okay, as the previous sessions, I have to tell the Professor Kabalji as well as Dr. Klex that all of you have time for about 40 minutes for your talks, and discussion will be open after all of you deliver your talk. That is at 12 o'clock, I think. Okay, we start with the talks delivered by Professor Kabalji. But before Professor Kabalji deliver his talk, I want to introduce him briefly. Okay, let me introduce Professor Kabalji. Professor Kabalji now is the Dean of the School of Engineering. He's from Department of Electronic Engineering at USAP University. I hope this is the right pronunciation. USAP, yeah, Prof. Okay, Turkey. Professor Kabalji got BSc from Selçuk University, Konya, and then from same university as well for his master degree in physics, and PhD degree from Istanbul Technical University, also in physics. Professor Kabalji, has good experience in material science, especially in the field of glass science and technology. He already synthesized a lot of works relating to glass for laser, that is glass doped with bismuth ion. Professor Kabalji teaching so many advanced physics in USAP University as well as at other universities like in Kazakhstan University. And I think that he has so many publications here, and I cannot read that one by one. Okay, Prof. Kabalji, you have 40 minutes. I'm sorry that Prof. Kabalji got problem with the camera, so Prof. Kabalji cannot turn on the camera. So, Prof. Kabalji, you have 40 minutes, Prof. And now time is yours, Prof.
Okay. Good morning to all of the distinguished participants, distinguished professor, researcher, and thank you very much for giving time and giving this opportunity to discuss the science and the research what's going on recently in the application of different areas. So today I would like to talk about the preparation and the spectroscopic properties of oxide-based optical glasses. Initially, it's my pleasure to talk about brief introduction to you about what's happening and what's the definition of the glass and the oxide glasses, classification of the glass materials as a amorphous structure. And I would like to share about some steps, preparation and the synthesis of the rare earth doped oxide glasses or undoped oxide-based optical glass materials. In addition to this brief introduction to the optical glass materials, I would like to give about the information about the thermal structure and the microstructure together with the kinetic and the spectroscopic measurements of the glass materials without doping materials or doped with various rare earth ions. In addition to these kinetic and spectroscopic measurements, how can we analyze the microstructure and what kind of methods should be applied to be able to define the crystallization structure. In addition to this, we need to determine which one is the best optimal value for the application in different devices. Means based on the photoluminescence and the decay time of the materials and the discussion about the result. As you know, glass materials could be doped with rare earth ions to be able to get a high refractive index ions or microcrystallite, which give it a great potential as a photonic application. The practical advances of this type of oxide or non-oxide glass materials, which are expected to have a significant roles in the many application from the optical fiber and the indoor application and also white LED application. So that is the reason we need to understand how can we classify this type of glass materials. As you can see here, glass might be grouped or classified into 3 groups. One of them is oxide glass materials. And the oxide glass materials, as you can see in this chart, also can be grouped or categorized into 2 groups. One of them is non-silicate glass materials, and the other is silicate materials. Non-silicate materials means based on the other chemical elements. One of them is bismuth-based glass materials, or telluride-based glass materials, or borate-based glass materials, phosphate, and the fluoride. So we can add account a lot. There are several non-silicate glass materials. And today, I'll try to share to you telluride optical glass materials. And the silicate glass materials, nowadays, it has been used in every application based on the silicium element. It means that the silica or silicium dioxide glass materials is also remarkable materials has been a lot of application in different area. So that is the reason this kind of silicate optical glass materials also can be used as a optical fiber. Nowadays, for the optical fiber has been also prepared and commercialized for the optical communication for internet connection information technologies. But in addition to silicate glasses, there is also organic polymeric glasses, and also there's a non-oxide glasses. In this categorization, there is like a chalcogenide glasses or halogen-based glasses or fluoride-based optical glasses. In addition to these brief classification of the optical glass materials, we can also define what is the structure of the glass and its structure. It means that as you know, as you mentioned, or as you familiar to the crystalline structure and the amorphous structure from the solid state physics, we can able to define the what is the structure of the glass. Glass materials is defined in the several literature. It means that it's a kind of an inorganic products of fission which has been cooled directly to the rigid condition without crystallization. It means that when you increase the heat prepared powder from the composite materials, so during the high temperature, we can able to quickly decrease the temperature, so the structure of the liquid couldn't find the time to become crystallization, and its structure change into the amorphous from the high temperature. So this kind of materials is also defined as a transparent optical glass structure, means amorphous structure. As you can see on the left hand side, when we compare the X and Y axis, volume and the temperature, there is a EM, it means that the melting temperature, and in this temperature, it's around, for example, over the 800 or 1100 degrees. For example, silicate-based glasses has a melting temperature over the 900, or actually it become liquid at 1500 degrees Celsius degrees. But in addition to silicate-based glasses, there is a borate-based glasses has a lower temperature than silicate at around 1200, or depends on the dopants composition materials. It can be moderate, nearly plus 100 or minus 100, 1200 or 1300 degrees can be shifted for the borate-based glasses. But for the low temperature glasses, sometimes we can also define it infrared glass structure, like a tellurium dioxide based glasses has a lower temperature than silicate, borate, or chalcogenide optical glass materials. Telluride glasses at around 800, 900, depends on the composition matrix. So it can be cooled down without crystallization. We can able to get the optical transparent plasma. This is the comparison of the amorphous structure and the crystalline structure. Again, from the atomic from the solid state physics and the solid state structure, the amorphous structure is random scattering of the atomic ion distribution in the glass structure. But in addition to this one, crystalline structure has a symmetry. So we know the symmetric points like cubic structure or tetragonal structure, like hexagonal structure. That kind of symmetry is change the optical properties and also some other electronic, magnetic structure of the metals. So this kind of definition should be explained for the optical glass materials. Furthermore, glass materials, as I earlier mentioned to you, might be doped with other ions from periodic table, periodicity. For example, nowadays, as you remember, erbium is one of the potential rare earth ions for optical fiber, which has been used and also commercialized for the internet and information technologies nowadays. So without erbium, for example, we cannot transfer the data or information from one point to other distance. So rare earth ions, which is really crucial for the optical fiber. We can able to define this kind of optical fiber like a polyoptical fiber or fiber gratings, structured fiber. So this kind of optical fiber and optical fiber amplifier, which has been used in integrated circuits elements also. So rare earth doped oxide glasses, it means that we can able to add in around the PPT ppm ratio. It means a very small composition concentration into the glass network. So by the way, we can able to change the optical properties of the glasses. It means that this kind of composition and concentration has an interaction between them, change the like absorption band gap and transmission band, also reflection. And so rare earth ion doped oxide glasses has a potential application, first of all, in fiber optic amplifier. For example, we can able to dope the glass with thulium, erbium, samarium, or other European rare ions. So, for example, thulium doped or erbium doped glass materials has also potential application in a fiber optical amplifier. It depends on the wavelength region. The second potential application area is infrared fiber laser at around 18 micrometer for the thulium. It means TM3 plus doped oxide glass materials. So also infrared fiber optics, one of them is a sensor, optical fiber, optical waveguide for VDM application. Also, white LED nowadays is a potential application of the amorphous structured optical glass materials. So why we need to do a lot of research about optical glass materials? Because of it has a different physical properties. So this kind of physical properties, it means that some of the oxide class materials has a low melting temperature, lower than silicate or borate or phosphate class materials. It means that this kind of low melting temperature based optical glass materials, for example, tellurium dioxide, one of them. So tellurium dioxide, due to the having a low temperature, so industrial companies might prefer, because of fabrication is easy and energy saving from the budget. So it has a potential, because high temperature means high energy, high cost. Secondly, this kind of low temperature optical glass materials has a high dielectric constant. It means that it has a second order refracting index and nonlinear optical properties. Third one is high refracting index, because, for example, silicate-based optical glass materials has a around 1.5, 1.4, 1.6 as a refracting index. But the tellurium dioxide, the chalcogenide, or depends on the how much ratio composition doped into the glass network, change, shift, increase or decrease the refractive index. So this kind of high refractive index is also important properties of the glass materials, and also resistance to atmospheric moisture. Resistance to atmospheric moisture is one of the best other physical properties. For example, P2O5 means phosphate-based glasses has a very sensitive to moisture at room temperature. P2O5 based optical glass materials could be more sticky and easy scattering under the electrification. It's really dangerous for the body and also environment. In addition to atmospheric moisture, transmission window in the infrared region is really wide than silicate. It means from the 200 to 7,000 nanometer wide band optical transmission based on the infrared glass materials. The other things is this kind of materials could be non-toxic and chemically also stable. It means it defined as a non-hygroscopic glass materials. High glass transition temperature, it also affects the glass tendency and easy glass structure. One of the important properties of the physical properties of the infrared glass materials is low phonon energies. As you can see in this group, for example, borate glass materials has a low phonon energies, 1400 centimeter or minus 1 is the largest than the other glass materials. Because this low phonon energy affect the excitation and emission and the relaxation between the convection and the valence band states. It means that the relaxation time and also photoluminescence and the luminescence quantum efficiencies of the glass materials. So phosphate is lower than borate glasses, silicate at around 1000 centimeter over minus 1. Germany is 900. Calibrated glass materials is, as you can see here, it is really smaller than the other glass materials. But chalcogenide and the fluoride is one of the best low phonon energy. They have one of the best low phonon energies. But the fluoride glasses I'm trying to mention here, it has toxic and hydrotropic properties. Chalcogenide glass materials is really 300 centimeter or minus low phonon, but chalcogenide glasses is not easy for application due to it has a high melting temperature, and transparency is not easily obtained from the networks. The chalcogenide glass materials based on the sulfur, selenium, like a semiconductor elements, excluding oxygen, like arsenic, germanium, antimonite, and the phosphorite gallium. This kind of chalcogenide glass materials has also potential application for optical phase change memory. It is an alternative of the magnetic memory. So optical phase change memory could be potential application for the future for the data saving. So this is the comparison and the explanation of the oxide glass materials. So as you can see here, when we have a look at the transmission of these some of the glass materials, so as you can see, silicate is lower than the other materials. Fluoride is larger than silicate, but the sulfide, like chalcogenide glass materials, it has also higher than silicate and the fluoride glasses when we have a look at the transmission. In addition to this one, telluride based glasses has also is good transmission band window. So this is the other advantages over these glass materials when we compare the structure. In addition to this one, we need to mention here optical fiber and the waveguide prepared and propagated in a different research center, because it's a lot of optical information technologies. Nowadays, we use it dominantly based on the optical fiber. Also, sometimes you can hear like 3G, 4G, 5G, like 4.5G is also based on the optical fiber structure. Means for telecommunication, and also optical communication is really based on the optical fiber. So optical fiber, as you remember from the electromagnetic theory or physics courses, which is a cylindrical waveguide made of the glass with a very low index contrast and a large core size. So the core is in glass center of the fiber, where the light is traveled by guiding. Over the core, there is a other thickness called by the cladding, defined as the cladding. It means that the outside optical materials surrounding the core. So, and the buffer coating, it means that this buffer coating for the optical fiber is also protect the structure from the environmental side effect. It means the plastic coating and the protective fiber. So the optical fiber depends on the numerical aperture based on the refracting index of core refracting index and the cladic refracting index. It means it depends on the critical angle. And the single optical mode fiber could be designed according to this numerical departure. So this kind of optical fiber can be prepared either core cladding or rod and tube, or by using the fusion techniques. Nowadays, some of the university and international commercial companies has been producing in a different optical fiber for optical communication. So this kind of application is also based on the pure glass structure. So, for example, silicium-based optical fiber nowadays has been used as a cladding, but for the core, could be included rare earth ions-based structured it means that in a different rare ions is in a different ratio inside. Ladies and gentlemen, so this is the synthesis of the tellurium based classes. It could be this is the class networks, and sometimes there's a class modifier, and tellurium dioxide sometimes not class modifier, and so this is the second part of the composition. Is a composition of the classes, and then it might be a increase of the number of the composition. So we can add some transition metal ions or alkali halides or semiconductor based materials into the structure. According to the calculation of the molecular ratio, for example, lead oxide or zinc oxide or lithium oxide, zinc oxide, titanium dioxide, or also we can add here some of the silicium oxide, aluminum oxide. So we can able to increase the number of the class composition for the preparation. So X is here is the molar ratio. The batch size can be weighted, can be prepared from 10 gram, 100 gram, 200 gram. How much class sample you need to prepare? It is possible for calculation and preparation. But we generally prepare the class materials from 15 gram, 20 gram, 10 gram, because as you know, for the characterization of the glass materials for X-ray diffraction, scanning electron microscope, or tunnelic electron microscope, transmission microscope, or Raman spectroscopy, just a small a piece of glass materials is sufficient for the measurement of the microstructure. For example, for SEM, just 10 milligram is glass. A piece of glass is enough for the measurement. But on the other hand, for the absorption, transmission, or reflection, just maybe for example, half centimeter or 1 centimeter bulk glass materials is sufficient for the measurement of the absorption or emission, and also lifetime or decay time photoluminescence of the glass materials. In addition to melting temperature for the tellurium oxide class materials, start from the 800, 900, or 1000, but above the 1000, when we dope with the other zinc oxide or magnesium oxide or calcium oxide, zinc chloride, this kind of material can be evaporated, depends on the temperature. So the melted liquids quickly quench between the graphite slab materials. So, for example, this kind of materials is prepared either in platinum crucible or aluminum crucible or ceramic crucible or carbon crucible for the different atmosphere, argon atmosphere or nitrogen or oxygen atmosphere in the furnaces. In this research, I try to share to you some of the oxide class materials, including lead chloride, doped with the tellurium oxide, or tellurium dioxide class materials with the zinc oxide and titanium oxide based class structure. For example, this is the ternary class materials based on the zinc oxide and the titanium dioxide oxide composition. The density, as you can see here, start at around 5.5 or 5.4. According to the increasing zinc oxide in the structure, the density is decreased at around 4.5 gram over the cube of the centimeter. So the density is also affected from composition. Density is also another physical properties should be measured to be able to calculate the intensity parameter or some photoluminescence parameter. Also, the structure is affected the emission and the absorption or section for the dopants. In addition to this one, for example, absorption and energy level, which is mainly steps to be able to understand the excitation and emission and the photoluminescence properties of the structure. As you can see here, this is the glass structure absorption spectra from the 400 to 1000 nanometer wavelength. It means that when we doped, for example, in a different rare earth ion ratio, might be changed from 0.2, 0.5, 1 mole, 2 mole, 3 mole, 4 mole. You can choose, but the rare earth ions is quite expensive than the other oxide powder. It means that the rare earth ion is helium dioxide, erbium dioxide, or samarium, neodymium oxide is really quite expensive materials to be able to get commercially from the companies. So that another, in addition to expensive cost, nevertheless, when you increase the thulium ions ratio in the glass networks, clustering can be seen in the structure. Due to the clustering, the absorption and emission or transmission affected. So the efficiency might be decreased. So, for example, thulium has a absorption band. This kind of ground level, excited level. So, and here there is a other absorption band can be calculated to be able to understand the excitation and emission and also emission cross section. So this kind of band area for each of absorption, we say absorption cross section should be precisely calculated to be able to understand the matrix elements for the strength of the transition. It means that, for example, 3H4, this kind of labeling based on the quantum physics. So we can able to understand this kind of classification of the absorption band in atomic structure. It means like a start level and Zeeman level under the electric field or magnetic field. So this is the shifting of the energy level of the thulium ions, as you can see here. So ground level and excited level. For example, when we excite these kind of ions under the 800 nanometer sources, so there's a two kind of emission band. One of them is a 1.47 micrometer. The second one is a 1.8 micrometer. So both of these has a potential application for fiber optic amplifier and the optical fiber intensity. So this is the important steps for the future steps. In addition to this one, I would like to show you the difference of the doped and undoped optical glass materials. For example, here, this is the undoped glass material. As you can see here, there is no here rare ions, only there is a absorption band, and also we can able to calculate this absorption band for 100 to 800 nanometer or 2000 nanometer just for the energy band gap. Means e.g. direct or indirect band gap band gap can be calculated from this absorption spectrum. So this kind of calculation is based on the equation absorbance theorized by the Mott and David equations. So it means that the absorption is considered either in doping or without doping to be able to calculate the optical properties. For example, here and okay, and then why the it shifted. Okay, I would like to show you this here. Now you see here the direct indirect band gap calculated from the Mott and Davis equation. So direct band gap, indirect band gap, we can able to calculate easily to be able to understand the radiation, non-radiation, and the optical properties of the glass materials. The second one is thermal properties. So thermal properties based on the differential thermal analysis for the optical glass materials. DTA or DSC give us thermal properties like a glass parameter, crystallization, and the melting temperature. And also these crystallization peak, it means that this crystallization peak is evaluated to be able to understand the enthalpy energy of the structure. It means that what type of crystallization can be seen inside, and the crystal growth and the crystal dimension can be calculated by using the differential thermal analysis based on some approximation like Ozawa approximation or Kissinger approximation. So, for example, this is the class forming tendency. Is other steps to be able to understand which one is the best potential candidate for your application. It means that you can prepare the 10, 20, 25, or at least a 5 or maximum 30 class sample, depends on the different composition, different concentration. But which one is suitable for your target? It means which one is the optimal material. How can we decide it? We need to understand the glass forming tendencies. And the crystallization kinetics, this is the Ozawa equation. As you can see here, crystallization number of the crystallization is calculated by cross-section of the crystallization peaks, means volume fraction, heating rate, and then we can able to find out the Aurami constant, depends on the crystallization dimension. And the Kissinger method is other semi approximation method to be able to understand the structure of the materials, to be able to calculate the activation energy by using the Kissinger equation. It means that how much energy is dissipated in the structure in a kilojoule per mole application. And for example, X-ray diffraction exactly explain us what kind of crystallization can be seen during the process of the materials. So we need to understand, but for optical fiber, we don't need any crystallization, because crystallization is damage the transparency and transmission and data transfer. So for the optical fiber, we are looking for one of the best materials without crystallization. Nevertheless, we need to determine the structure, microstructure, by using the X-ray diffraction of the glass materials. For example, by using the SEM and EDX, we can able to understand the surface crystallization either in cross-sectional crystallization, because this is the unwanted structure. But nevertheless, we can do research by exposure, heating rate, and yield glass sample. We can able to understand the cross-sectional crystallization can be seen, or surface crystallization is the dominant for your glass materials. So this is the absorption cross-section again for the doped with the thulium ions, and energy level of the thulium ions depends on the because of this kind of thulium ions, 4F energy level is protected, shielded under the other energy level. That's the reason emission and the relaxation time could be different from others. But to be able to calculate these kind of optical properties, we use also Jadot theory. Jadot theory is considered the four transition, means in German language, grade and grade, based on the Russell standards definition. Briefly, Jadot theory give us, first of all, intensity parameter, and also radiative transition probabilities. Is depends on the depends on the angular momentum, and also radiative lifetime tau or measured lifetime by using the experimental step. And then finally, we can able to calculate the luminescence quantum efficiency and also branching ratio of the structure. In these steps, luminescence quantum efficiency is really important step as a result, because by calculation of the quantum efficiency, you can able to define which one is the potential materials for your target application. So this is the theory of the from quantum physics, Einstein and coefficients, is spontaneous emission, stimulated emission, and absorption transition. Why we need to understand these kind of materials? Because laser or lasing is depends on the Einstein coefficient. We can able to understand only just calculation of these kind of absorption, stimulated, and cross section. This Jadot theory is theoretical, and measured parameter is calculated by using the Lambert-Beer law and the matrix elements, and then the irreducible tensor operator, and also the refracting index, the density, and then finally we can able to calculate the radiative lifetime, branching ratio, and the beta. Beta is here, branching ratio, and yes, I am going to finish in 5 minutes. And also luminescence measurement has a setup like excited by diode laser, chopper, and spectrometer, and then you can able to calculate the luminescence. By using this luminescence, we can able to calculate the effect of the cross relaxation rate, depends on the concentration for the different classes. And lifetime also can be measured either in your laser experimental setups or commercial devices. It give rise to measurements of the lifetime. Luminescence lifetime means decay rate for the different concentration. And analysis of the data, it means that the measured decay rate or radiative decay rate or non-radiative decay rate, all of these kind of parameter could be calculated by using the decay time and the photoluminescence measured. This is the lifetime measurements. For example, according to this, all the data is calculated and obtained materials. For example, which of the concentration is the best for your preparation, 1 mole or 2 mole or 3 mole. So you can decide, and then you can get the optimal value for the spectroscopic measurement. This is the, again, lifetime measurements, quantum efficiency. So as you can see here, which type of energy emission is the best evaluated for your application, and what kind of composition is efficient for your future planning. I mean, 10 mole percent, 20 mole percent, 40 mole percent. So you can prepare several glass sample. Which one is more suitable as a application? Ladies and gentlemen, as a conclusion, oxide-based glasses has been going on research, depends on the composition, concentration, in a different application, optical fiber, waveguide, a sensor, or white LED, or just indoor application. It means that it is categorized in a different group. This kind of borate oxide or silicon oxide or tellurium can be increased as a glass network. So density, absorption, energy band could be calculated. Structure should be evaluated. The structure should be evaluated because also hardness, now micro hardness, also scratchable glasses, elastic glasses should be evaluated. For example, elastic glasses, it means that I think LG or Samsung still also going on research on the thin glasses, means flexible glasses for the electronic application or screen, touch screen. So this kind of application needs to do more research on the elasticity, viscosity of the glass materials. Crystalline structure should be evaluated. Optical structure should be also evaluated. So in this research area, still or research is going on. Different oxide like a borate optical glasses, tellurium dioxide glasses, and also based on the bismuth oxide glass materials. As a result, we have a good collaboration with the Istanbul Technical University and also in China, in South China University of Technology, Professor Dr. Minyu King, Professor Dr. Gönül, and from Czech Republic, Academy of Science Czech, Dr. Cirizavadil and Dr. Peter Koska, and also in Turkey, Dr. Neşe Öztürk. We have a good collaboration. Also, Professor Dr. Ahmet Marzuki is our international partnership. We are still has a good cooperation. Thank you very much for your listening. And finally, I will try to share to you from my hometown. This is my hometown in Turkey. So it is a small city. It means that my city, Kahramanmaraş, is east of Mediterranean seaside. Okay. Thank you very much for your listening and attention.
Okay, thank you very much, Prof. Kapalji. Nice talks. And ladies and gentlemen, so Prof. Kapalji have delivered an aspect of TM class for various applications as well, and all aspects required in order to could make, for example, good optical fiber and then good blood waveguide. So, for example, they have to avoid crystallization. And what is he also explained how to generate, for example, the emission spectra that required, for example, at between 1400 till 1600s. So he already discussed this very well. And ladies and gentlemen, if you have any questions, please write down your question, and because we will open that question after Professor Francis Klex deliver his talk. So thank you very much, Prof. Kapalji, and we will open the questions 40 minutes after this. Okay, thank you very much. Ladies and gentlemen, we go to the next talks, and this talk will be delivered by Dr. Francis Klex. He's from Sheffield Hallam University in United Kingdom. So before Dr. Klex deliver his talks, I want to introduce him briefly. So Prof. Francis Clegg is a principal research fellow. Is fellow in Sheffield Hallam University, and he got his PhD from Sheffield Hallam University, applied chemistry, and got PhD from Sheffield Hallam University as well. And he's a very active researcher and won many research fundings. And there are so many papers as well, as Professor Kapalsi does now. So, Prof. Francis Clegg, will you deliver by yourself, or maybe from video, because the committee have got a video from you? Good morning from Prof. Francis Clegg. How are you?
Good morning. Thank you for the invitation.
So,
can you hear me okay?
Okay, yes, good. How are you?
I'm good, thank you. Yeah.
Okay. Prof, will you deliver your talk with your video? Yeah, there's the committee now already got that video, or you will deliver by yourself?
I think a video will be better because the internet connection isn't brilliant here. Is that okay?
Okay, thank you very much, Prof. Time is yours now. You can open your video or you can deliver by yourself. Okay, Prof.
Can you see the video?
Yes, you can see that.
And can you hear the video?
Yes. Oh, there's no sound. I cannot hear your voice, Dr. Clegg.
Okay.
Okay, yeah, I can hear that now.
1 second.
Sorry, Mr. Ahmad Marzuki, or maybe the committee will have for the video.
Yeah, I think the committee have the video. If you can play it from your side, that would be better.
Okay, bro. Okay, bro.
Maybe we will share the video
please come with
by the committee.
You can turn on the video for Dr. Francis Clegg.
Okay.
Can start turn on that video, please.
Okay, we still prepare it. Wait a second.
Hello, my name is Francis Clegg, and thank you.
Okay, can you hear the
I'm
sound?
from Sheffield, which is the United Kingdom. You may not have heard of Sheffield, but it's about 150 miles north of London. Today, I'd like to talk about polymer nanocomposites, and it's a topic I've been researching for the last 20 years and within a variety of different applications. So what are polymer nanocomposites? They're simply polymers which contain fillers that have at least one dimension in the nanometer scale. So they offer the ability to enhance a range of different properties and often several at the same time. These could be mechanical, barrier, thermal stability, or flame retardancy. The fillers can be different shapes, as shown here, spherical, sheet, or tube. And my work has mostly focused on clay and graphene-based materials. So what are clays and which are best to use? So there are lots of different types of clay. Here we see a range of different types that are ordered with respect to the size that they grow to and the layer charge. They're mostly platy materials, and where we see stacks of clay layers. So kaolinite talc, vermiculite mica, more commonly called clays that people may be more aware of, but we're mostly interested in bentonites and hectorites. And this is simply because they're much more easy to disperse in polymers than the other types of clays present. So here we see the clay chemical structure for montmorillonite and hectorite. For montmorillonite, we see that we have one clay layer, which is made up of one aluminium octahedral sheet sandwiched between two silicon tetrahedral sheets. Some of the aluminium 3+ cations are substituted by iron 2+ or magnesium 2+ in the negative charge, and that charge is compensated by exchangeable cations present within the interlayer space. These could be sodium or calcium cations. Hectorite has a similar structure, but rather than aluminium in the octahedral sheet, we see magnesium, and some of these magnesium cations are substituted by lithium plus cations to create that net negative charge. So remember that one layer is made up of 3 sheets. One layer for a montmorillonite is approximately 1 nanometer thick, and these platelets can have dimensions up to about 200 nanometers or maybe up to 1 micron, depending on the type of clay and how it's grown, manufactured. So how the clays are dispersed within a polymer is important. This diagram on the left describes how clays can be dispersed in the polymers. You can see that the clays are stacks of layers. Think of a deck of playing cards. And these can be dispersed in the polymer as stacks and described as microcomposites. We can also get polymer chains entering between the clay layers. And if we have still an ordered system here, then we can call them intercalated nanocomposites. Whereas if there's lots of polymer between the clay layers are disordered and randomly arranged, then we call that an exfoliated nanocomposite. This is a very simplistic description. It's a bit more complicated. For example, we can get shearing of these plates to give high aspect ratios. And the clay stacks are not perfect. They will be staggered, more staggered rather than uniformly placed on top of each other. We can also get scenarios like this, in particular in aqueous systems, where we get what's called a house of cards structure, where the edges interact with the faces of the interlayers. So that's a bit of a description about clays and nanocomposites. And I've used these in several research applications. And the last time I came to Indonesia, back in 2015, I talked about a sustainable flexible packaging material. This was a starch-based coating, which was coating on paper or paperboard. The starch gave inherently good oxygen barrier, and with the inclusion of clay, we were able to considerably improve the water vapor barrier properties. And in this research, we assessed several different sources of bentonites, and we were able to understand why some behaved well and others didn't. And it had a lot to do with the layer charge and its distribution on the clay surface. This affected the way that the clay interacted with the starch and the plasticizer, and ultimately the clay dispersion within the starch. A recent project I've been doing, looking at, involves clay and graphene oxide in waterproof garments. So waterproof garments are important in hard or snowy, windy conditions, as in this photograph here. So waterproof membranes can be monolithic or microporous. This example in the SE image is microporous, and they're designed to let water vapor from inside the jacket pass out, i.e. that produced by sweat, but to also stop water coming into the jacket, i.e. that from rain or snow. And we've been looking at how clays and graphene oxides can change the breathability and waterproofness of these garments. In the microporous form, we can use these nanofillers to change to control the size of the pores and the thickness of the walls, and also the pores and the sizes of the pores on the outer surfaces of the membranes too. So as part of this study, we've used variable focus microscopy to quantify the roughness and porosity of the membrane surface. So it's not an easy task to do with these samples. And we were at the limit of the instrument, the sensitivity of the instrument. SEM certainly gives nice images, but not necessarily a measure of the roughness. And roughness is important for understanding the wettability measurements and water contact angle measurements. I've also looked at the use of clay and graphene on the flame retardancy of polymers. One particular project looked at the use of a sustainable biopolymer as a replacement for phenolic resins that are used to make structural components. An example of these structural components is aircraft furniture. Clays or graphene themselves alone don't always make a big difference on the flame retardancy, but when combined with traditional flame retardants, they can synergistically work together so that less flame retardant is needed. So this is ideal for improving or keeping the properties of the polymer. Adding the nanofillers can also improve the mechanical and other properties too. So ultimately, one can produce a lightweight component, which will be good for saving fuel, for example. So flame retardancy, they work by producing a carbonaceous char. As the polymer is burned away, the clay layers remain and they become stuck together with this carbonaceous char. This stops the heat and oxygen penetrating into the bulk of the polymer, and this reduces the amount of volatile degradation products. These volatile degradation products are also stopped from exiting from the polymer, and it's these volatile products that create the flame and fuel the flame. So we can stop that, we can help it to be a better flame retardant. There are two projects I'd like to talk about in more detail using nanofillers. One is about wound dressings, the other is about injectable hydrogels. So first of all, I will discuss wound dressings. But the start of this project, about 10 years ago, it would be fair to say that I didn't know much about antimicrobial wound dressings. However, fortunately, some of my university colleagues did, and through interacting with these, we were able to pool our ideas together and start this project. So we called ourselves the IN crowd, quite a trendy name, but it stood for iodine nanocomposite controlled release open wound dressings. So Chris Breed and myself, we were the material experts. Neil Brickeblank, he'd had expertise and use had done research in iodine complexes previously. Keith Miller was the microbiologist. Louise was a registered pharmacist who had a lot of involvement before joining the university in the NHS with distribution of wound dressings. It was the start of her PhD that started this project off. And Lukasz and Marianne, they helped with making and characterizing these wound dressings. So this slide serves as a warning because the next slide shows some infected wounds and the challenge that we are trying to address. So if you're squeamish, then just please look to one side for the moment. So I've not put these photos on simply to shock, though they are quite shocking. For me, it just shows how bad infected wounds can be and the challenge we face. But then remember that they not only look gruesome, but they often smell too. So it's not a pleasant experience for the patient. There are a high number of people infected across the world, and this can result in death. And the consequences and the treatment is very costly. Okay, so maybe about 50 billion in the US. And the rise in diabetes and an aging population will just means that these numbers and figures will increase in the future. So it's a problem we need to fix now. Another warning, the next slide also shows infected wounds, but perhaps not as bad as the others. So how do wounds get infected? Basically, there's bacteria everywhere, and there are good and bad bacteria. When we have damaged skin, then the bacteria can invade the wound, come from our skin and also other surfaces. The growth of this bacteria leads to high concentrations of bacteria, and often in the form of biofilms. These have an extracellular mechanism, and these can significantly delay healing. So these bacteria can cause damage via toxic enzymes and waste products, and basically it becomes more difficult for the body to heal itself. So yeah, infection of the wound can cause tissue death, systematic. We also need to be aware of antibiotic-resistant bacteria. One such example is MRSA, which is a particular strain of Staphylococcus aureus, which is resistant to the antibiotic methicillin. It means that these types of infections become more harder to treat. So it's a problem we have to cope with. So where did this project start? There are several wound dressings that are commercially available. Louise, she evaluated several. So silver, iodine, honey, and polyhexanide dressings. And they were okay, some of them, but we couldn't identify any with a sustainable controlled release. So those that tested, we found that they typically dumped or they released their active agents really quickly, within a day. Okay. And what we wanted was to create a controlled release mechanism, something that could last longer than one day. So the advantage of this would be that the dressing would remain on the wound for longer. So it means you'd have less dressing changes, which means reduction in costs, but also more importantly, it would mean less disruption to the healing process. So if you remove the dressing, it causes damage in that process. It changes the temperature and the pH of the wound, and it delays the healing. And it can also cause reinfection as well. So that's the reason we wanted a controlled release open wound dressing. So with the knowledge that there's no known bacteria that are resistant to iodine, we designed some formulations based around this, and we tested them. I'm not going to describe this graph, this table. I just want to highlight that we looked at quite a wide range of different formulations, more than what's presented here. And from these experiments, we established a few things. So we established that we needed two polymers. Polymer 1, PVPI, which is polyvinyl pyrrolidine iodine. This was the most effective as our source of iodine. We needed polymer 2 to give the dressing some mechanical integrity. We also found that we needed clays for obtaining that dressing integrity and robustness. We also noticed that we need clays to provide us with that sustained release mechanism. This little cartoon on the bottom just shows that if we have clay layers within the dressing, that any active agents simply take a lot longer to elute or escape from the dressing due to that tortuosity effect. Okay, so this is a simple test to demonstrate the sustained release. We coated some of the dressings on glass slides, and then we added this to a beaker of deionized water. After 24 hours, we took that glass slide out and put it into a fresh, clean time period. What we can see that when we have low clay, all of the iodine was released within a very short period, compared to when we have higher clay, the iodine release was sustained release. So adding that clay gave us that sustained release that we really wanted. So after all that work, we came up with a standard material. With this standard material, we could produce quite large sizes. It was flexible, so it could make good contact with the wound. It's also self-stratified. You can see there are two distinct layers. You can see that by the color on this photograph here. And depending on which layer was placed onto the wound, it gave different, or placed down, it would determine which rate, it would determine the rate of iodine release. So one was quicker than the other. And this activity lasted for up to 4 days. I'll describe what that means later. But first, I just want to describe a bit more about this material. So we could physically separate these two layers with a knife or scalpel. We see that the top layers are darker and there was less of this. About nearly 40% of it was the dark layer, nearly 60% the light layer. We found that there was less clay in the top layer. There's also less PVP and iodine in the top layer, but there were equal amounts of polymer 2 in the lower and the upper layers. We think the more clay in the bottom, partly due to some sedimentation effect, also a preferred complex with the PVPI also. So we got a good understanding of what this material was like. We can use X-ray diffraction on the samples to assess how the clay is dispersed. Don't want to talk too much detail about this, but the despacing beat gives us an indication about despacing. And for most of the samples, we strongly suspect that an integrated system was obtained. We use Raman spectroscopy to determine the active iodine species. What we saw that there are potentially many different species of iodine possible, but we only observed 2 species, that's I3- and the I5-. Fortunately, these are the active species of iodine. We found that I3 was predominantly associated with PVPI, but with the polymer 2, we got both I3- and I5- interacting with the polymers. Lots of other studies showed us that the quantity of the clay or the processing method species present. So when I said the dressing has up to 4 days or more activity, this is how we tested it. We did some in vitro growth inhibition assays. What we do is we take some of the dressing, 2 centimeters square bit of dressing, we sterilize that dressing, and then we place it on an inoculated agar plate. And what happens is, over time, the antimicrobial iodine leaches out of the dressing and kills the blood, kills the bugs, the bacteria. And what you notice that you see a clear zone. This is also known as zone of inhibition. So what we do is we measure this zone of inhibition. We do it 5 times, take the average, and after 24 hours, we pass it onto a new inoculated plate and over again. So we see how long the activity lasts for. So we tested a range of common wound bacteria: E. coli, Pseudomonas aeruginosa, Staphylococcus aureus, and some MRSA strains too. And what the results showed is that they can be effective up to 4 days, if not 7 days for some bacteria, whereas the commercial dressings probably only lasted 1 or 2 days maximum. So we've achieved that sustained release. It's interesting that we get different profiles for different bacteria, so they must consume or interact with iodine at different rates. And what we do observe is this peak after 48 hours. So there are possibly several mechanisms going on here in the process of the experiment. What we need to just come away with is that the release rate can be controlled by adding the amount of iodine, the different amounts of iodine, and we can see that the inhibition zone, as indicated by this red arrow, increases as we increase the amount of iodine. It also shows that we can control the release rate by the inclusion of clay. As we increase the amount of clay, that zone of inhibition gets smaller, telling us that the clay is reducing the amount of iodine being released. So we can control the relative release by the amount of clay. So to conclude this project, 4 days, there is a stratification of the composite film. We get different release rates depending on the way we face that dressing onto the agar. We can make large sizes, which are quite flexible. The text here at the bottom sort of supports the use of iodine over commonly used silver dressings. And the main point really being that iodine has a much wider spectrum of activity because there is no known bacteria that are resistant to iodine. Whereas with silver, they don't kill all bacteria. Okay, so that's the wound dressing project. So the next detailed project I'd like to talk about is the injectable hydrogels. Okay. So this research began with my colleagues. They produced an injectable hydrogel that, when cooled, formed a solid hydrogel. This video shows that. It shows that also that the temperature which solidification compress the flame over quite a narrow temperature range. So we can see that we have a white liquid at 39 degrees centigrade. But as soon as we inject it and it's cooled to the surrounding 37 degrees centigrade, then it becomes this translucent solid. Okay, so we can see that solid there. So how do we make these? What's happening? We take the monomer, we disperse our allayed silicate within that monomer system. We thermally initiate that polymer system to produce our polymerized liquid. We can cool that liquid, but when it goes below the LCST, which is the lower critical solution temperature, it then forms this hydrogel. In that process, the polymer chains go from a globule nature to a coil type nature. Once we've gone to this coil type nature, the interactions occur and it's not reversible. Can't go back to a processable liquid. At the processable liquid stage, we can add active ingredients such as stem cells. And the reason we're interested at 37 degrees centigrade is that's the temperature of the body, and we can utilize these materials within the body. So one such example, or potential example, is for vertebral disc degeneration. This can happen through disease or general aging or wear and tear as we get older. So here at the top, we see quite a healthy disc in which the nucleus pulposa is healthy. Where at the bottom, we can see that there's degenerations occurring here. We've got holes in there, and it's is to inject the hydrogel into the nucleus pulposa. The hydrogel will provide the support required within the disc, and if stem cells are introduced, then they can potentially provide regeneration of this disc. So this video shows, demonstrates how the liquid becomes solid after injection. I've just made a hole within this gel. The hydrogel has had a dye added to it, so we can see what's happening more clearly. The hydrogel was at a higher temperature than the gel, so it's now cooled down within the gel. And as you can see, it's filled them gaps within the holes that were created by the needle, and it's solidified to form that gel. So where are my colleagues up to at the moment? They have material that has tunable properties. These mechanical properties are comparable to those of the human nucleus pulposa. It has a storage modulus of about 3 to 5 kilopascals. They've done some studies on using goat vertebral discs, and what they've done, these tests are done under axial load, so they replicate the stresses and strains experienced within the spine of the human. And what we can see after 3 weeks is that the fissures that have been produced, that have been created in the nucleus pulposa are still filled, and they remain intact. Interestingly, the type of pressure that's given onto the stem cells encourages the stem cells to produce different types of cells. That's a really interesting fact. So where did I come into this? I'm interested in clays and layered silicates and how they behave. So we wanted to understand how different clays would behave in these materials. So previous to this, we've only really investigated one type of laponite, which is a synthetic hectorite before. So laponites come in platelet sizes and different cation exchange capacities, i.e. the layer charges on the surface. We see that FN has got the highest platelet size and the highest cation exchange capacity, whereas RD, for example, has got the lowest of those. We also compared to bentonite, which was chlorite sodium, which is quite a clean bentonite, so it's predominantly montmorillonite present. Okay. So, what do they look like? This is what they look like above the LCST temperature. They're all white looking. And already we can see that the larger platelet sizes, i.e. FN and OG, they produce quite hard elastic blocks, whereas the smaller layered silicate platelets either produce very soft flowing material or a soft gel in the absence of anything. When we cool down, we can see that the white nature has become more translucent, and the extent of transparency gives us an indication of how the clay is interacting with the polymer. If we compare the transparency to the layered silicates just in water in the absence of any polymer. And we can see that with RD and XL21, that transparency is maintained, whereas with EL, it has become more cloudy. With FN, which is in water is the most cloudy, doesn't necessarily produce the most cloudy gel when in the presence of the polymer. That relies with OG. So we can already see that there are different polymer laponite interactions that are occurring. If we take these cooled down hydrogels and dry them by placing them in the oven to remove the water, we can analyze these by X-ray diffraction and infrared. So it's quite difficult to do this, and partly because some of the layered silicates don't have a strong D-spacing, and also the polymer also has a reflection in the same region as you look as the D-spacing reflection, so it's quite difficult to interpret it. But generally, most of them we think are exfoliated, but there is the exception with the FN, in which there was possibly an integrated or a micro-composite structure still present. Silicate dispersion by FTIR. If you consider the structure of the montmorillonite or hectorite, we have some in-plane silicon-oxygen bonds and we have some out-of-plane silicon-oxygen bonds. And these are in unique. When the layers are stacked, we get broad bands, but when separated by integration or by water, then the bands change. For hectorite, we see two distinct bands, whereas for montmorillonite, we see the fourth band intensity decreases and the band 2 increases as the clay layer separation occurs. So in infrared, this is the data. This area is what we're looking for. So indeed, it does tell us that the layered silicate layers have separated, but it has potentially separated. The intensity is much stronger than for FN and the XL21. This is indicating that the dispersion is not as good, or they're not as well separated. And with the chlorite, we see that we do get good separation there. So to summarize, the X-ray diffraction and the FTIR generally agree with each other. So that's reassuring, and it gives us an indication about how these layers are interacting with the polymers. One interesting way to assess the polymer layered silicate interactions is to look at the structures formed after first freezing in liquid nitrogen and then freeze drying. So these structures are not present in the hydrated form, but do occur through that drying process. And we can see that there are quite big differences. So EL and RD, they give big pores, and these are the ones with the smallest platelet sizes. FN produces a flake-like structure. OG gives like an internal pore-like structures where we have thick walls, and within these walls there are smaller pores. And with XL21, much smaller pores we observe. So we know that they're interacting differently. If we look at as we measure the pore sizes, then we can see capacity. As the cation exchange capacity increases, then that pore size generally decreases. We can also control the pore size by increasing the amount of clay and our layered silicate, and that generally leads to a decrease in the pore size as we increase the amount of layered silicate present. We've done viscosity measurements on this data. It gives us a quantification of the strength of the gels formed. Data is collected from right to left as the sample is cooled. And what we see as we go through that LCST temperature, the gels become stronger. And as the platelet size increases, that LCST slightly shifts to a lower temperature too. We can look at the storage and loss modulus. Again, the data collected from right to left as the temperature's cooled. Generally, we see an increase in the loss modulus as the temperature's increased, as temperature is cooled, and this results from the polymer chains going from that globule to that coil configuration. The extent to which this happens correlates with the platelet size and with the bigger differences with the smaller platelets. And so generally, we also see stronger gels with these larger platelets. This is on a log scale, so these are quite big differences. Okay. So to summarize, the nature of these hydrosols can be controlled by the type of lapidary we use and the concentrations. The observations can be correlated to the cation exchange capacity and the platelet size, but there are other layered silicate characteristics that we need to consider. We hope to do some TEM studies to confirm that layered silicate dispersion, and we've also been investigating other polymers, but this is a story for another day. I'd like to gel and also Hassan Judda, because he did all the hard work. This was his PhD project. So I'd like to finish by thanking you all for the invitation and your attention. And if you have any questions, and I'll be very happy to ask. If you want to email me, then please do so.
Okay, thank you very much, Dr. Francis Klex, and also for very nice talks. It is, I think, it's very good presentations, and also this good knowledge for us, yeah, for everybody coming into this conference. Okay, thank you very much, Dr. Francis Klex. Ladies and gentlemen, now we have maybe 10 minutes, yeah, for discussions, I think. So if you have any questions, please write down in column chat, or maybe raise your hands, and don't forget to say to whom that question is addressed to. Okay, question answer is now open.
Sir.
Okay. Sri Mulciani, okay, I think you can directly convey your questions, please.
Okay, thank you very much, Dr. Marzuki. So my question is addressed to Professor Kleck, Francis Kleck. Am I right? How to spell it? Hello. Hello. So I'm very interested in your research concerning the stem cell. Okay, so I would like to get the knowledge how to do the stem cell. Is it we have to? I mean, we have to add some cell from other cell, for example, like I mean, there is also some culture media used for stem cell method. The mechanism, I mean, the techniques for stem cell.
Okay, the stem cells is not my area.
Oh, okay.
It's not my area of expertise, but you can extract stem cells from the body. Okay. What's interesting with the stem cells is that these stem cells, when they're in different environments, will grow differently. So when they're in the spine, for example, if they undergo certain different pressures and temperatures, etc., the stem cells will grow into different types of cells. So different types of nucleus pulposa cells, etc. So I would have to refer you to my colleagues about where you can get stem cells from. So I'm a materials scientist, and my colleagues are the biomedical people. So sorry.
Okay, thank you. So one more question only. Is it is it possible if we add some like polymer, synthetic polymer? No, I mean, as you mentioned also in your PowerPoint presentations that you mentioned like monomerilonate, clays and bentonite and everything. We can do also these materials for stem cell. Is it possible or not?
So they are compatible with stem cells. They're not toxic. Some are toxic and some aren't. With the laponites, these are synthetic clays, so they're manufactured in the factory or and so you can make them clean and you can make them without contamination, and therefore they can be compatible with the body and non-toxic. Okay.
Okay.
Yeah.
Okay. Thank you very much, professors. Thank you.
Thank you for your question.
Okay. Thank you very much, Sri Abdul. Okay, now next question, please. We still go maybe 5 minutes or 3 minutes left. Is there any more question?
Mr. Ahmad, we have a question in the chat box.
Okay, in chat box, yeah.
Okay. So I think there's a question from Anas. And
Okay.
it's talking about when only plasticizer enter the clay gallery, it will create the pore water barrier properties, while opposite when both polymer and plasticizers enter the gallery. This is what are the name of the plasticizers. The plasticizers we used were polyethylene glycols. We investigated a lot of different types of plasticizers, glycerol, triacetate, but we did find that polyethylene glycol was the best. And we only looked at starch. There are lots of different types of starches, and there are potato type starches, corn starches. We found the best results were coming from the potato starches. Okay.
Okay, that's the answer from Dr. Franz Flex. We got 2 minutes left. If is there any more questions, please? Is there any more questions?
There's one from Aldila.
Yeah, from Aldila.
Yeah. Good afternoon, sir.
Yeah.
Hello,
Okay.
yes. My name is Aldila from UNS. I want to ask something about what is the important application of TM dot class?
Application of what?
For whose?
For
Professor Kapalci, yeah?
Yeah.
Yeah, okay. Okay, Prof. Kapalci, there is a question from Aldila regarding with the importance of TM2 plus, yeah? Okay. Okay, Prof. Kapalci. Halo, Prof. Kapalci. Prof. Kapalci, I think okay, maybe Prof. Kapalci maybe we can contact him maybe. So okay. Hello, Prof. Kapalci. Yeah, maybe he's still doing something. Maybe he can solve up. Okay. Maybe is there any question for Dr. Francis Flex? Okay, additional elements. I have to say thank you very much to Professor Francis Flex and also Prof. Kapalci, because you know that we have limited time for this discussion. But if for example we still have any questions, I think.
Mr. Ahmad, we still have one. Yeah, we still have one question.
What is the function of clay in? Okay, that's for Dr. Franz Flex. Okay, that's one question for you, Dr. flags. So what is
So
the function of clay in hydrogel wound dressings?
So the function of the clay is multiple, actually. So firstly, the clay is there to slow down the release of the iodine. So it helps us with the controlled release. If you think about the clay layers in the polymer, any active ingredient has to travel around these barriers. So it simply slows down the release of the active agent. But it also allows the compatibility between the two different polymers that we used. If there's no clay, the two different polymers completely separate and are immiscible. But with the clay, they combine the two polymers together, and they also create that stratification process. So the clays are quite important in the integrity and the slow release of the active ingredients in the dressing.
Okay, he said, okay, who is the Mr. Darsono, yeah, from Darsono. Okay, if there is no more questions, I have to close this session, and I have to say thank you very much to Dr. Francis Klex and also Professor Idris Kavalci for sharing very valuable knowledge, yeah, to the conference participants this year, and I hope we can maybe discuss, maybe we can invite you maybe in the next session, and also I hope that every participant, maybe if you have any question, maybe and you're interested in this topic, maybe you can contact Dr. Francis Klex in Hallam University. Is that all right, Dr. Klex? Yeah. Right?
Yes. Any questions? Please email me. Yes, I'm happy to answer any questions.
And also possible collaborations, Dr. Klex. Yeah.
Thank you.
Okay. And that's also applied to Professor Idris Kavalci. So once again, thank you very much, Professor Kavalci and also Dr. Klex, for your very, very great talks today in this conference. Okay, thank you very much. And now time back to MC. Thank you very much, Prof. Kavalci and Dr. Klex.
Thank you.
Okay, thank you, Mr. Ahmad Marzuki, and also our amazing speakers, Dr. Idris Kavalci and Dr. Francis Klex. Ladies and gentlemen, we are now at the end of the plenary lecture, and the next agenda will be the panel session, which begins at 1 p.m. We give many thanks to all of our incredible speakers for today's plenary session, and to all participants. You may leave the Zoom meeting and please be back at 12:55 p.m. See you and have a nice rest.